On the 4th day of October, 2025, an image originating from the Martian surface irrevocably altered our understanding. The sophisticated Perseverance rover documented a phenomenon in the sky above Mars. This was no mere speck, no indistinct blur, but rather a distinctly shaped luminous entity, its length measuring approximately 4 times its width. The global internet, predictably, erupted into a frenzy. Within a mere handful of hours, 2 distinct perspectives emerged. On one side, a luminary from Harvard, Avi Loeb, proposed a logical, albeit mundane, explanation: a photographic anomaly, a product of composite imaging that created a visual deception. Contrarily, Dr. Horace Drew, a scientist with a distinguished background at Caltech and in Cambridge, asserted that the physics did not align. His argument posited that if a halo of green nickel compounds were indeed encasing the object, then the core ought to exhibit a green hue as well. However, the captured image clearly displayed a white center. The situation escalated further into profound strangeness. NASA abruptly ceased all communication. Subsequently, the European Space Agency followed suit, then China, a nation known for its strategic release of Martian imagery for public relations purposes, and finally, the United Arab Emirates. Here we have 4 distinct space exploration entities, often at odds on the global stage, all simultaneously refraining from disclosing what their respective Mars-orbiting satellites had observed during the most intimate of celestial rendezvous in history. Consider the timing. NASA's governmental funding lapse commenced on the 1st of October, a mere 48 hours prior to this critical observation period. A rather convenient coincidence, some might say. Presently, as the celestial body known as 3I Atlas hurtles towards the Sun, with its perihelion anticipated on the 29th of October, we are confronted with 2 primary probabilities. Either we are witnessing an unprecedented celestial visitor, a comet unlike any previously documented, exuding industrial-grade nickel alloys and defying all conventional scientific explanations, or something far more extraordinary is unfolding in the Martian atmosphere. In this presentation, we will dissect the evidence that both factions are reluctant to reveal: the photographic records, the deliberate silence, the peculiar anomalies, and the compelling reasons why the 29th of October may prove to be a pivotal date for humanity. If this subject ignites your curiosity as much as it has mine, kindly engage the like button and subscribe to remain informed. Furthermore, I invite you to share your geographical location and the current time where you are, along with your preferred explanation, be it the photographic artifact or a more profound enigma, in the comments section below. To bolster our growing community, please consider sharing this content across platforms such as X, Facebook, Reddit, or your preferred messaging application. Your steadfast support is deeply appreciated. Chapter 1: The Images That Reshaped Everything. Let us embark on this journey from what feels like its genesis for a vast majority of us. October the 4th, 2025. This date stands poised to be etched into history, either as a pivotal moment in human comprehension or as another instance where our imaginations outpaced verifiable facts. The ultimate judgment remains pending, and it is precisely this uncertainty that imbues this event with such profound intrigue. The Perseverance rover, strategically positioned within Jezero crater on Mars, had been assigned a rather extraordinary task. For several preceding days, mission controllers on Earth had been meticulously preparing for this singular moment. The 3rd confirmed celestial body of interstellar origin ever detected, identified as 3I Atlas, was executing its closest orbital pass to Mars. Though separated by a distance of 38 million kilometers, this proximity, in cosmic proportions, was akin to a brief, intimate encounter. This presented humanity with an unparalleled opportunity to meticulously examine an entity originating from beyond the confines of our solar system. From the immense, star-speckled void between galaxies, a region where our probes have never ventured, where we have never captured an image, and where our understanding of its potential inhabitants remains profoundly limited. The rover's navigation camera, commonly referred to as NavCam, commenced its scheduled sequence of captures. These are not the high-fidelity color instruments responsible for the breathtaking panoramas of the Martian landscape. The NavCam serves a more functional purpose, designed to assist the rover in charting its course, circumventing obstacles, and facilitating its traversal across the ochre terrain. It records imagery in monochrome, possessing an angular resolution of 33 milliradians per pixel. These technical specifications possess limited significance until one comprehends their implication at a distance of 38 million kilometers, approximately 12,500 kilometers per pixel. Pause for a moment to consider this. Each individual pixel within the captured image encompasses an area exceeding the diameter of Earth itself. Consequently, fine details are rendered imperceptible. One cannot discern the intricacies of spacecraft design or decipher serial numbers. However, the general form of an object should be discernible, particularly when multiple images are aggregated to mitigate noise and amplify the discernible signal. And this is precisely what transpired. The Perseverance mission team, or perhaps more accurately, a collective of dedicated amateur astrophotographers who diligently monitor the raw data feeds, began to meticulously combine the NavCam frames. This was not a simple superposition of 2 or 3 images, but rather hundreds of them, acquired over an interval of approximately 10 minutes of Martian time. This stacking procedure is a widely adopted technique in astrophotography. When attempting to capture faint celestial phenomena, the aggregation of multiple exposures proves invaluable. Random noise tends to cancel itself out, while genuine signals are amplified. This is how amateur astronomers capture nebulae with their backyard telescopes, and how professional researchers manage to resolve the most distant galaxies at the observable universe's periphery. Upon the integration of these images, an unexpected form materialized. It was not a circular point of light, nor a nebulous cloud trailing behind it like every comet historically observed from Earth. Instead, a linear feature emerged, an elongated shape approximately 4 times longer than it was wide, radiating luminescence against the backdrop of stars. Critically, it presented a distinct white coloration at its core, with subtle hints of green at its peripheries. The image disseminated across social media platforms with astonishing rapidity, reaching global audiences within hours. Discussions on Reddit forums intensified, generating hundreds of thousands of comments. The platform, formerly known as Twitter, became a vibrant hub for discussions involving amateur astronomers, proponents of conspiracy theories, professional scientists, and individuals from all walks of life, all eagerly contributing their perspectives. YouTube channels immediately dedicated themselves to analyzing the pixel data, enhancing contrast levels, and drawing definitive conclusions. At the epicenter of this global discourse lay a question, deceptively simple in its phrasing, yet carrying an immense weight of implication. What precisely are we observing? The prevailing explanation was disseminated with remarkable swiftness. Avi Loeb, a distinguished professor of astrophysics at Harvard and the director of the Galileo Project, had been closely monitoring 3I Atlas since its initial discovery in July. He had previously authored scholarly articles suggesting that the object exhibited peculiar characteristics, anomalies that deviated from the conventional profile of a typical comet. However, as the Perseverance image gained widespread traction, accompanied by public queries regarding its potential depiction of a cylindrical extraterrestrial vessel, Loeb published a detailed explanation on his personal blog, outlining his interpretation of the event. He attributed the observed elongation not to alien technology, but to fundamental principles of physics and the operational mechanics of camera systems when capturing moving objects. 3I Atlas was traversing at an approximate velocity of 67 kilometers per second relative to the Sun, following a retrograde orbital path, essentially moving in the opposite direction to Mars's own orbital motion. From the Martian perspective, the object was hurtling across the celestial sphere. Over a 10-minute interval, it would have covered a distance of roughly 50,000 kilometers. When aggregating hundreds of individual frames captured during this temporal span, the outcome is effectively a time-lapse sequence. The object's motion is effectively smeared across the final composite image, thereby fabricating the illusion of elongation. This phenomenon is analogous to photographing an automobile in motion at night using a prolonged exposure setting. The vehicle itself may possess a compact form, but in the resulting photograph, it appears as a luminous streak stretched across the frame. The vehicle's headlights and taillights leave luminous trails. One would not logically conclude that the automobile's actual shape is that of a ribbon simply because the photograph depicts it as such. Loeb meticulously calculated the relevant parameters. The NavCam's angular resolution indicated that each pixel corresponded to a region of 12,500 kilometers at 3I Atlas's observed distance. The observed streak measured approximately 50,000 kilometers in length. Dividing this distance by the object's velocity relative to Mars, which, considering their combined motions, approximates to 91 kilometers per second, yields an interval of roughly 9 to 10 minutes. This time frame precisely aligned with the required integration period for stacking a sufficient number of frames to elevate the faint object's signal above the background noise threshold. The mathematical calculations substantiated his hypothesis. The proposed explanation was both elegant and straightforward, grounded in well-established principles of imaging and motion dynamics. A conclusive resolution, one might assume. Not for everyone. Dr. Horace Drew, widely recognized online by the pseudonym Red Collie, is an individual whose pronouncements command considerable attention. His professional credentials include significant contributions at Caltech and the MRC Laboratory of Molecular Biology in Cambridge. His research has encompassed diverse fields, including DNA, enigmatic crop formations, and what he characterizes as extraterrestrial coding. While some perceive him as a maverick, unafraid to explore unconventional concepts, shunned by the mainstream scientific community, others view his endeavors as having ventured too far into speculative realms. Nevertheless, his counterargument to Loeb's explanation resonated significantly, primarily because it focused on observable evidence present within the images themselves. Drew highlighted a crucial detail observable in the enhanced, colorized versions of the stacked images. The central portion of the elongated feature appeared white, while the edges exhibited a distinct greenish tint. He argued that this observation was consistent with Earth-based telescopic observations of 3I Atlas, which revealed a greenish coma, a diffuse envelope of gas and dust surrounding the object's nucleus, indicative of nickel-rich compounds. His contention was that if the elongation were solely an artifact derived from stacking images of a small rocky body moving through a pervasive green coma, then the resultant composite image, created by aligning frames laterally, should predominantly display a green hue. The accumulated green emission from the coma within each individual frame would be substantial enough that the final stacked image could not possibly retain a conspicuously white central region. This would only be possible, Drew proposed, if the object itself possessed an inherent, extended white structure, what he termed an exile structure, that significantly surpassed the dimensions of the surrounding green coma. In such a scenario, the process of image stacking would preserve the white dominance in the central area, owing to the greater proportion of white material compared to green within each constituent frame. This constitutes a geometric argument pertaining to ratios and the manner in which colors integrate during the image stacking process. This line of reasoning is not easily refuted without undertaking intricate simulations, precisely quantifying the extent and intensity of the coma at that specific distance, modeling its appearance in the NavCam's monochromatic captures, subsequently colorized, and accurately determining the nucleus's actual size and configuration. Drew further emphasized that multiple orbital spacecraft from various nations had captured imagery during the flyby event. These included the Mars Reconnaissance Orbiter, Mars Express, the ExoMars Trace Gas Orbiter, China's Tianwen-1, and the UAE's Hope probe. All of these instruments were directed towards 3I Atlas during its closest proximity on October the 3rd. Despite this, as of October the 6th, when Drew and his contemporaries were disseminating their analyses, not a single officially processed image had been released by any of the involved space agencies. The raw data from the Perseverance NavCam were publicly accessible, a consequence of NASA's automatic posting protocols. However, the high-resolution images anticipated from HiRISE, the camera aboard the Mars Reconnaissance Orbiter, possessing a resolution of 30 kilometers per pixel at 3I Atlas's distance, remained undisclosed. The spectroscopic data, crucial for elucidating the coma's chemical composition, the color imagery acquired by the CASIS instrument on ExoMars, and the infrared observations from the Hope probe, all of this critical information was withheld from public view. The prevailing question became, why such a prolonged silence? NASA's official explanation was direct and unambiguous. The United States federal government had entered a period of shutdown on October the 1st, precisely 2 days before the critical flyby observation window. A considerable number of NASA personnel were placed on furlough, resulting in the suspension of website updates and the cessation of press release generation. The agency, in its own words, was operating with a significantly reduced workforce, prioritizing only those activities deemed absolutely essential for mission continuity. The processing and dissemination of images pertaining to an interstellar comet, irrespective of its scientific import, was apparently not categorized as a mission-critical function during this budgetary impasse. However, the confluence of these events struck many as conspicuously suspicious. A governmental shutdown commencing precisely 48 hours prior to what was anticipated to be one of the most significant astronomical events in recent memory. This timing appeared almost too coincidental, and it failed to account for the analogous reticence from the European Space Agency, an organization operating independently of American budgetary politics. Nor did it explain the silence from China, a nation that routinely publishes images from its Mars missions as a demonstration of national pride and technological prowess. Furthermore, it did not elucidate why the UAE, keenly interested in showcasing the triumphant achievements of its Hope Mars mission, the pioneering Arab interplanetary probe, had not eagerly seized the opportunity to present the world with the data captured by its instruments. This was not an isolated instance of sluggishness from a single entity. It represented a coordinated reticence spanning multiple geopolitical rivals, nations that actively compete for prestige, funding, and influence within the realm of space exploration. And it was this pervasive silence more so than any single photograph that ultimately became the dominant narrative. Because in the stark absence of official data, speculation inevitably rushed in to fill the void. And with 3i Atlas, there was already a fertile ground for such conjecture. Chapter 2. Two possibilities, one underlying truth. The ensuing debate evolved into a highly charged intellectual contest, unfolding not within the measured confines of peer-reviewed journals, with their protracted review processes, but rather in real time across blogs, digital social platforms, and hastily convened video conferences. This was an unusual trajectory for the field of astronomy. Typically, observations are meticulously gathered, data is subjected to rigorous analysis, scholarly papers are drafted, submitted, revised, and subsequently published. This methodical process demands considerable time and unwavering patience. Peer review serves as a critical safeguard, ensuring that errors are identified, alternative hypotheses are thoroughly examined, and conclusions are unequivocally supported by empirical evidence. However, 3i Atlas offered no such temporal luxury. The object was in constant motion. With each passing day, it traversed millions of kilometers, steadily approaching October the 29th. Following this celestial encounter, it was projected to alter its trajectory and commence its outward journey from the solar system, accelerating as it receded from the sun's gravitational influence, ultimately to depart our celestial neighborhood permanently. The window of opportunity for observation, for data acquisition, for discerning its true nature, was rapidly diminishing. Consequently, the debate unfolded at an accelerated pace, with scientists, amateur astronomers, and interested observers all contributing their perspectives concurrently. The fundamental question appeared deceptively straightforward. Was the elongated appearance observed in the Perseverance images a genuine physical characteristic of 3i Atlas? Or was it merely an optical illusion, a consequence of the image acquisition and processing methodologies employed? To fully appreciate the significance of this distinction, one must grasp the profound implications of each potential answer. If the elongation is indeed a photographic artifact, then 3i Atlas is likely a comparatively diminutive celestial body, perhaps measuring only a few kilometers across, enveloped by a diffuse envelope of gas and dust. While undoubtedly unusual, given its interstellar origin and peculiar chemical composition, it would fundamentally be classified as a comet. Its chemistry might be peculiar, its trajectory certainly anomalous, yet it would remain a naturally occurring object, formed in another star system billions of years ago, subsequently ejected through gravitational interactions, and now serendipitously traversing our solar system. Conversely, if the elongation is not an artifact, if the object genuinely exhibits an elongated physical structure, then the conversation shifts dramatically. Natural celestial bodies tend to adopt specific forms. Smaller entities often possess irregular shapes, akin to asteroids, due to insufficient gravitational force to induce spherical collapse. Larger celestial bodies naturally assume spherical or oblate spheroid configurations if they are rotating at high speeds. Elongation ratios of 4:1 are exceptionally rare among natural formations. While not entirely impossible, such a shape would necessitate highly specific formation conditions or material compositions capable of withstanding gravitational pressures or tidal forces. An elongated structure immediately invites a comparison to Oumuamua, the very first confirmed interstellar object discovered in 2017. Oumuamua was also observed to be elongated, with estimates suggesting a ratio of approximately 10:1 based on variations in its brightness as it tumbled through space. This observed elongation fueled an enduring scientific debate. Some posited it was a cigar-shaped asteroid. Others suggested it might be a flattened disk viewed from its edge, resembling a pancake. And Avi Loeb himself controversially proposed the possibility of it being a solar sail, an incredibly thin, artificial construct propelled by the pressure of starlight. Oumuamua's elongation, coupled with its non-gravitational acceleration as it departed the solar system, an acceleration that could not be fully accounted for by the outgassing typical of comets, rendered it highly anomalous. The scientific consensus largely converged on exotic yet natural explanations, such as the emission of invisible hydrogen gas or the sublimation of solid nitrogen ice under unusual conditions. However, the debate surrounding Oumuamua never reached a definitive conclusion, and Loeb continued to advocate for the consideration of artificial origins until empirical evidence conclusively ruled them out. Now, here was 3I Atlas, potentially exhibiting similar elongated characteristics. If this elongation were a genuine property, it would represent the second highly elongated interstellar object detected out of only 3 such discoveries to date. This establishes a significant pattern. 2 out of 3 instances equate to approximately 67%. If elongated shapes are uncommon among natural celestial bodies, but appear with notable frequency among interstellar visitors, a critical question arises. Why? What distinguishes interstellar objects? Are we observing a selection bias, where only certain forms are capable of surviving ejection from their home systems and the arduous journey through interstellar space? Or are we, perhaps, witnessing something entirely different? The mathematical arguments became increasingly intricate. Numerous astrophysicists, not directly involved in the exchange between Loeb and Drew, initiated their own simulation studies. By modeling 3I Atlas as a point source, essentially treating it as a star, and subsequently tracking the predicted path of that point across the Martian sky over a 10-minute interval, it became possible to generate synthetic images. Each positional data point was then blurred to account for the navcam's resolution, and these blurred points were stacked. The outcome of these simulations generally supported the artifact explanation. A moving point source, when tracked and aggregated, naturally produces an elongated streak. The length of this streak corresponds directly to the distance traveled during the total exposure time. This is a fundamental application of kinematics combined with image processing techniques. However, these simulations relied on certain assumptions. They presupposed that 3I Atlas was a point-like entity, with its luminosity concentrated within a small nucleus. What if the coma, the diffuse envelope surrounding the nucleus, were extensive? What if it already spanned dozens or even hundreds of kilometers at that observed distance? In such a scenario, each individual frame would not capture a discrete point, but rather a fuzzy disk. The aggregation of multiple fuzzy disks over time produces a different result compared to the aggregation of points. The resultant streak becomes smeared and less sharply defined. The distribution of brightness also undergoes alteration. And this is where the situation becomes particularly intriguing. The captured images revealed relatively well-defined edges for the elongated feature. While not perfectly sharp, they were noticeably sharper than one might anticipate if the images were indeed derived from the aggregation of a large, diffuse coma traversing the frame. This degree of sharpness suggested either a smaller than expected coma, a nucleus possessing a higher intrinsic brightness relative to its coma, or indeed, a structural elongation of the object itself. Furthermore, the analysis of color presented another compelling point. Drew's observation regarding the white central region juxtaposed with the green-tinged edges was not easily dismissed. Other amateur astronomers began to retrieve and analyze their own ground-based observational data, acquired in early September when 3I Atlas was photographed during a total lunar eclipse. These images, captured using tracking telescopes calibrated to compensate for the object's motion, depicted 3I Atlas as possessing an apparently extended white core surrounded by a greenish halo. Gerald Raymond, an astrophotographer with decades of experience in imaging comets, noted that the observed structure appeared atypical. Most comets exhibit a bright nucleus from which a coma gradually fades, typically assuming a circular or slightly elongated form directed away from the sun due to solar radiation pressure pushing dust particles outwards. The visual presentation of 3I Atlas in his captured images differed significantly. The white region appeared elongated even when accounting for its motion, and the green coma seemed to form a distinct layer around this central core, rather than a uniform luminous diffusion. If these ground-based observations were considered valid, they implied that the white, elongated appearance was not exclusively an artifact of the Perseverance imaging process. It was already discernible from Earth, albeit rendered more challenging to perceive due to the vastly greater distance and atmospheric distortion. Professional astronomers began to interject with notes of caution. Several pointed out that accurately determining the true shape of a comet, whether observed from Earth or from Martian orbit, is inherently fraught with observational challenges. We are not directly perceiving the solid nucleus. Instead, we are observing sunlight that has been scattered by the dust and gas particles enveloping the nucleus. The distribution of this particulate matter is contingent upon the manner in which the nucleus is outgassing, which, in turn, is influenced by its rotational characteristics, the composition of its surface, the angle of incident sunlight, and a multitude of other environmental factors. A spherical nucleus exhibiting uneven outgassing from active regions can indeed generate asymmetric comas that may appear elongated. However, other astronomers noted that 3I Atlas had already demonstrated a multitude of unusual properties beyond the mere debate over its shape. And it is at this juncture that the conversation begins to broaden, extending beyond a simple dichotomy of two potential explanations. The issue of chemical composition continued to be a prominent point of discussion. Observations conducted from space by the James Webb Space Telescope in early August had revealed an unexpected finding. The majority of comets are rich in water ice. As they approach the sun, this water sublimes from the surface, generating the characteristic tails observed. However, 3I Atlas presented a marked departure from this typical behavior. A spectrographic analysis revealed the comet's coma was primarily composed of carbon dioxide, not water. Specifically, it comprised 87% carbon dioxide by mass, with 9% carbon monoxide and a mere 4% water. This ratio, an 8-to-1 proportion of carbon dioxide to water, was highly unusual. Comets originating within our solar system typically exhibit the inverse ratio, showing a significantly greater abundance of water than carbon dioxide. While some comets from the distant Oort cloud, the farthest reaches of our solar system, have demonstrated higher levels of carbon dioxide, none have approached the proportions seen in this object. The only other known interstellar comet, 2I Borisov, displayed a water-dominated chemistry mirroring that of solar system comets. The question arose, why was 3I Atlas so devoid of water? One hypothesis posited that if the comet formed in a frigid region of its home star system, far from its star, then its water ice might have been depleted early in its history, leaving the carbon dioxide intact. Alternatively, prolonged exposure to cosmic rays during its billions of years' journey through interstellar space could have altered its surface composition. However, another chemical anomaly further deepened the enigma. Observations from the Very Large Telescope in Chile detected nickel atoms within the coma. While the presence of nickel in comets is not inherently surprising, with many comets exhibiting trace amounts of metals, 3I Atlas was generating nickel at an extraordinary rate. Critically, this production of nickel occurred without a corresponding presence of iron. In natural processes, nickel and iron are inextricably linked. They originate together in the cores of collapsing stars, are ejected into space simultaneously during supernova events, and condense into planets and asteroids as a pair. Every celestial rock sample analyzed, from meteorites to asteroid fragments, consistently shows nickel and iron in remarkably similar proportions. These elements share chemical similarities, bonding with similar materials, and do not naturally separate under typical conditions, except through industrial refinement processes. On Earth, we isolate nickel from iron when pure nickel is required for specialized alloys, protective coatings, or high-temperature applications, such as nickel plating or the nickel-based superalloys used in jet engines and spacecraft components. These advanced technologies necessitate the separation of nickel from iron through chemical or electrochemical methods. The data from the Very Large Telescope indicated a dramatic increase in nickel emission as 3I Atlas drew nearer to the Sun. Within a single month, from July to August, its production rate escalated by a factor of 25. This steep ascent, following a power law relationship with the Sun's distance, suggested that something on the comet's surface was being heated and preferentially releasing nickel. Plausible natural explanations were considered. Perhaps nickel carbonyl compounds, rare molecules in space, were sublimating from the surface, while iron compounds remained stable, an unprecedented but not physically impossible scenario. Another possibility was a layered surface composition, with nickel-rich minerals on top and iron-rich materials beneath, where only the uppermost layer reached temperatures sufficient for metal release. Nevertheless, a more sensational, headline-grabbing explanation emerged. The nickel signature closely resembled that expected from manufactured materials. If 3I Atlas were artificial, possessing a metallic hull or structural elements, nickel alloys would be a logical choice due to their durability, radiation resistance, and stability across a wide temperature range, qualities ideal for an interstellar probe. However, attributing an object's artificial nature, based solely on its chemical composition, represents a significant leap, demanding exceptional evidence. To date, all observations could still be plausibly, albeit awkwardly, explained by natural phenomena, albeit peculiar ones that had not been previously observed. This is precisely what makes interstellar objects so fascinating. They are samples from alien planetary systems, places beyond our reach, where conditions may have differed considerably from those during our solar system's formation. The debate regarding whether the object's perceived elongation was a genuine characteristic or an observational artifact remained unresolved, as both sides presented compelling arguments that resisted easy dismissal. Underlying this ongoing discussion was a growing awareness that the visual imagery constituted only a portion of the narrative. The chemical analyses, too, were incomplete. Equally crucial was the information that was conspicuously absent, the data that should have been disseminated but was withheld, the observations made by multiple space agencies that they declined to share. A palpable silence seemed to intensify with each passing day. Chapter 3. The Deafening Silence. The peculiar nature of silence is that it only becomes truly noticeable when an expectation of sound is present. In an era characterized by constant social media updates and competitive space agencies vying for public attention, a collective silence from multiple organizations simultaneously becomes profoundly noticeable. Consider the established communication practices of China's National Space Administration. Since its Tianwen-1 Mars orbiter entered orbit in the year 2021, the agency has released over 14,000 images. These are not mere raw data. They are meticulously processed, aesthetically rendered visuals accompanied by official statements, often strategically timed to coincide with national holidays or to highlight China's burgeoning spacefaring capabilities. When Tianwen-1 captured a comprehensive color map of Mars at a resolution of 76 meters per pixel, the images were made public within days. Similarly, when the accompanying rover, Zhurong, successfully landed on the Martian surface and commenced transmitting photographic data, China ensured its immediate global dissemination. This approach is not uncommon. Space agencies leverage their achievements to justify budgetary allocations, inspire future generations of scientists and engineers, and demonstrate their technological prowess. During the Cold War, the space race between the United States and the Soviet Union was as much a theater of propaganda as it was a scientific endeavor. Every satellite launch, every crewed spaceflight, every lunar landing served as a powerful declaration of capability and advancement. This competition, while evolving, has never truly ceased. Today, China and the United States perceive each other as primary rivals in space exploration. The Artemis Accords, an American-led framework for lunar exploration, explicitly excludes China. In response, China has forged an alliance with Russia to jointly plan an international lunar research station. Direct collaboration between these two space powers is minimal. The Wolf Amendment, enacted by the U.S. Congress in the year 2011, explicitly prohibits NASA from engaging in bilateral cooperation with China without specific authorization. Consequently, data sharing and collaborative efforts are virtually non-existent. The focus is on competition. Therefore, when 3I Atlas made its closest approach to Mars, presenting both NASA's Mars Reconnaissance Orbiter and China's Tianwen-1 with ideal vantage points for observation, one would anticipate each agency to eagerly publish their findings. The hypothetical headlines would be remarkable. China captures unprecedented images of interstellar visitor, or NASA's HiRISE delivers clearest view yet of mysterious comet. Such scientific milestones are highly beneficial both domestically and internationally, justifying funding and generating widespread excitement. Yet, neither agency released anything. No processed images, no preliminary analyses, not even a concise statement confirming successful observations. NASA cited the ongoing government shutdown, a genuine circumstance that furloughed thousands of employees. However, the shutdown did not impede the Perseverance rover from continuing to automatically upload raw navigation camera images, as these are transmitted through automated systems that operate independently of human intervention, as part of the mission's data management protocols. If raw navigation camera images could still be posted, why were raw high-resolution images from HiRISE withheld? And why, operating entirely independently of American budgetary politics, did China fail to release any data from Tianwen-1? The United Arab Emirates introduced another layer to this perplexing situation. Their Hope orbiter, part of the Emirates Mars mission, was specifically designed to study the Martian atmosphere across diurnal and seasonal cycles. It is equipped with 3 instruments, including the Emirates Mars Infrared Spectrometer and the Emirates Mars Ultraviolet Spectrometer, ideal tools for analyzing a comet's coma, detecting chemical signatures, and measuring the interaction of gases with solar radiation. Hope possessed a clear line of sight to 3I Atlas during the October 3rd flyby. The UAE has consistently expressed immense pride in the Hope mission, which marked the Arab world's inaugural interplanetary endeavor, arriving at Mars in February of the year 2021. The mission team regularly disseminates data, issues updates, and actively engages with the public. The UAE Space Agency maintains a robust social media presence, celebrating its accomplishments and sharing its scientific discoveries. However, following the October 3rd flyby, a notable silence ensued. No images of 3I Atlas, no spectroscopic data, and no mention of observations beyond a brief pre-flyby statement confirming impending observations. It was as if these events had, from their perspective, not occurred. Despite months of anticipation, the European Space Agency presented yet another puzzle. Its Mars Express and ExoMars Trace gas orbiter were both strategically positioned to conduct observations. In September, ESA had announced that observations would take place between the 1st and the 7th of October, specifying that Mars Express would utilize its high-resolution stereo camera and spectrometers, while the Trace gas orbiter would employ its color and stereo surface imaging system and its own suite of instruments. These were not casual observations. They represented planned, scheduled, and coordinated efforts involving multiple teams across various European nations. And then, silence. The ESA website offered no updates regarding 3I Atlas observations beyond the initial announcement. No press releases, no preliminary findings, no images were published. For an agency that routinely shares spectacular imagery of Mars and publishes findings from its numerous missions with consistent regularity, this absence felt deliberate. As observers began to highlight this coordinated silence spanning geopolitical divides, certain historical parallels emerged. There have been instances where rival nations have collaborated on matters of shared interest. The Partial Nuclear Test Ban Treaty of 1963, signed by the United States, the Soviet Union, and the United Kingdom at the height of the Cold War, acknowledged that atmospheric nuclear testing posed a threat to all nations, irrespective of their political ideologies. Space rescue agreements subsequently followed. The Apollo-Soyuz test project in 1975 saw American and Soviet spacecraft dock in orbit, with crews shaking hands in space, while their respective nations remained ideologically opposed on Earth. The common thread uniting these instances was the presence of shared existential stakes. When an event threatens everyone equally or impacts the entire species, rivalry often recedes in importance before the imperatives of survival or understanding. The 1998 United Nations Office for Outer Space Affairs established guidelines, though not binding treaties, concerning how nations should approach the detection of extraterrestrial intelligence. These protocols emphasize that no single nation should issue unilateral announcements. Confirmation must be verified, and the international community must be informed. Premature disclosure, it was argued, could potentially trigger public panic, widespread misinformation, or international incidents. If, and this is a significant stipulation, the Mars orbiters had indeed observed something that fundamentally challenged the assumption of 3I Atlas being a natural object, then a scenario of coordinated silence could be logically constructed. This would not imply a conspiracy, but rather adherence to protocol, a measure of caution, and an effort to verify findings before making pronouncements that could not be retracted. However, this line of reasoning necessitates the belief that something extraordinary was observed, and as the adage goes, extraordinary claims require extraordinary evidence. The silence itself does not constitute evidence of anything beyond the fact that images have not been released. Mundane explanations are certainly possible. Data processing requires time. Quality control necessitates meticulous review, and scientists often prefer to publish findings in peer-reviewed journals rather than through immediate press releases to maintain credibility and secure priority of discovery. Government shutdowns, even partial ones, can disrupt workflows and delay publications. Nevertheless, the persistent pattern remained troubling. 5 space agencies, representing the United States, Europe, China, and the United Arab Emirates, all possessing operational Mars missions, all positioned to observe the same celestial event, and all opting not to share their results in the immediate aftermath. 5 agencies that typically do not coordinate, often competing for prestige and funding, were suddenly united in their reticence. Online communities began to meticulously track this situation. Threads on Reddit forums such as r/space and r/astronomy accumulated hundreds of comments, dissecting every conceivable angle. Users noted that Tianwen-1 routinely posted images within 48 to 72 hours of acquisition. They pointed out that ESA had shared Mars Express images mere days after capture. Furthermore, in previous instances, the UAE's HOPE mission had established a public data portal specifically designed for transparency. One individual observed that on October 1st, just 2 days prior to the flyby, China's Tianwen-2 mission, an entirely separate spacecraft en route to collect samples from an asteroid, released a selfie image displaying Earth in the background. This was a calculated propaganda piece, aesthetically composed, featuring China's flag on the spacecraft against the backdrop of our planet. The timing of this release struck observers as significant, demonstrating China's capability to publish space imagery during the precise time frame when 3I Atlas observations should have been processed. Instead, they chose to release a Tianwen-2 image and deliberately withheld Tianwen-1 observations of the interstellar visitor. The question arose, was this choice meaningful, or was it an instance of pattern recognition in random data, perceiving conspiracy where only coincidence existed? The pervasive silence fueled rampant speculation. Some argued that all the agencies observed nothing remarkable, that 3I Atlas appeared precisely as anticipated, a typical comet, and therefore there was no urgency to rush preliminary results to the press when comprehensive papers could be meticulously prepared. However, this explanation failed to account for why China would not leverage even mundane observations for the sake of national prestige. Others suggested technical malfunctions, positing that all the relevant instruments had simultaneously failed, although the probability of such an occurrence seemed exceedingly low. More provocative theories proposed deliberate suppression, suggesting that high-resolution images had revealed structural elements or geometric configurations that could not be readily attributed to natural processes. According to these theories, spectrographic data indicated chemical signatures inconsistent with any known comet. It was hypothesized that multiple agencies recognized they were observing something requiring coordinated announcement, if an announcement were to be made at all. One blogger meticulously compiled a timeline illustrating that within 72 hours following the October 3rd flyby, various government officials and scientists had appeared on news programs discussing 3I Atlas. Jay LeBeau, for instance, was interviewed on Newsmax, sharing the screen with Representative Tim Burchett, a member of the House Committee on Oversight and Accountability. In a separate news segment, Stephen Miller, the Deputy Chief of Staff for Policy at the White House, was directly questioned regarding whether the president had been briefed on 3I Atlas. Miller provided a diplomatic and vague response, assuring the public that relevant agencies were monitoring the situation, but offering no specific details about briefings or findings. The mere fact that White House officials were being queried about an astronomical object, that it had escalated to the level of presidential briefings, suggested that the matter was being taken seriously at levels far beyond mere scientific curiosity. The participation of a congressional representative on television to discuss the object, the direct questions posed to White House staff regarding 3I Atlas, and the media's coverage of it as a developing story rather than a simple scientific curiosity all pointed towards an event that had transcended the realm of typical astronomical observations. Yet, the core data remained inaccessible. The high-resolution images, capable of resolving features 30 kilometers across at 3I Atlas's closest approach distance, would have definitively indicated whether the object's brightness stemmed from a massive nucleus or an alternative source. They would have revealed actual structural details, if any existed, and would have either resolved or intensified the ongoing debates about its elongation, its shape, and its fundamental nature. These images existed. They had been captured. Somewhere within NASA's databases, on servers that had remained operational despite the shutdown, the highest resolution photographs of an interstellar object ever taken by human instruments were stored, either processed or awaiting processing, and yet they were not being shared with the world. The silence persisted. Days passed, October 6th, October 7th. Speculation intensified within this vacuum of information, and while the world awaited official images that never materialized, another peculiarity of 3I Atlas began to attract attention. This phenomenon was observable in amateur observations captured before the comet disappeared from Earth's perspective behind the Sun. It was something that added yet another layer of mystery to an already perplexing celestial body. A color change from red to green, a transformation that defied immediate explanation. Chapter 4. The enigmatic green glow. Color in astronomy serves as a crucial source of information. When a celestial object appears red, blue, green, or any other hue, it conveys details about its composition, temperature, and the processes occurring on or within it. Sunlight, being white, encompasses all visible wavelengths. When this white light interacts with a comet, certain wavelengths are absorbed by molecules in the coma, while others are re-emitted through fluorescence. The color perceived is a direct chemical signature of the object's constituents. Green comets are not exceptionally rare. Many comets develop a greenish luminescence as they approach the Sun, and the underlying cause is well understood. A molecule known as diatomic carbon, represented chemically as C2, forms when larger carbon-containing molecules within the coma are dissociated by ultraviolet solar radiation. This C2 molecule absorbs ultraviolet light and subsequently re-emits it at specific wavelengths within the green portion of the spectrum, around 510 nanometers. This process is remarkably common, and astronomers anticipate observing it in active comets composed of carbon-rich materials. 3I Atlas was extensively observed throughout July and early August. During this period, it presented a reddish appearance. This reddish hue indicated that dust particles were reflecting sunlight with a slight bias towards longer wavelengths. This observation was consistent with a comet situated far from the Sun, where sublimation was minimal, and the coma consisted primarily of dust grains gently released from the warming nucleus. The red color signified a normal, dust-dominated composition. Then, on September 7, 2025, a total lunar eclipse occurred, visible from specific locations on Earth, including Namibia. During a total lunar eclipse, the moon traverses Earth's shadow, resulting in a sky significantly darker than that of a typical full moon night. This darkness creates ideal conditions for observing faint celestial objects without the obscuring glare of moonlight, offering astronomers a valuable window of opportunity for clearer viewing without the necessity of waiting for a new moon. Two experienced astrophotographers, Michael Yeager and Gerald Riemann, were positioned in Namibia with their equipment trained on 3I Atlas. Both had decades of experience imaging comets and possessed a thorough understanding of their typical behavior and the colors they usually exhibited at varying distances from the sun. Their telescopes tracked 3I Atlas across the night sky, compensating for Earth's rotation and the comet's motion to maintain its position at the center of long-exposure photographs. Upon processing their captured images, a striking transformation became evident. 3I Atlas was no longer reddish. It glowed with a distinct green hue, an emerald-tinted luminescence that extended into a coma measuring approximately 2.5 arc minutes in diameter. The color shift was dramatic and unambiguous, transitioning from one hue to another within a span of mere weeks. Yeager posted the images online, accompanied by a caption noting the green to blue-green gas coma and mentioning the visibility of a faint tail in images taken on September 9th. The astronomy community immediately took notice. This color change from red to green signaled an increase in the comet's activity, indicating that gases were now dominating the coma rather than solely dust. It suggested that 3I Atlas was entering a more active phase as solar heating intensified. However, this is where the situation becomes truly peculiar. When researchers examined the spectroscopic readings, specifically the detailed breakdown of which wavelengths were being emitted, they found a striking lack of diatomic carbon in significant quantities. Multiple research groups had successfully captured spectra of comet C2019Y4 Atlas during late August and early September, utilizing advanced professional telescopes. A scientific paper authored by Luis Salazar Manzano and his colleagues at the University of Michigan focused precisely on this anomaly. They observed an exceptionally low proportion of C2 molecules compared to cyanogen, CN. This ratio was so remarkably diminished that they concluded Comet Atlas was among the most depleted comets ever documented in terms of carbon chain molecules. Consider this. The comet presented a distinctly green visual appearance, strongly indicating fluorescence from diatomic carbon. Yet, the spectroscopic analysis revealed that the very molecule responsible for that vivid green glow was, for all intents and purposes, absent. It was akin to observing smoke without a visible flame, or hearing the chime of a bell that remained silent. The phenomenon was evident, but its presumed origin was missing. Several hypotheses were put forward to account for this discrepancy. One explanation centered on the timing and the specific locations from which the observations were made. It was theorized that C2 might have been present, albeit in very small concentrations, and that the green luminescence was being produced with such high efficiency that it remained visible even with depleted C2 levels. The efficiency of fluorescence can fluctuate. A minimal quantity of a highly effective fluorescent substance can indeed generate a perceptible glow. Another possibility suggested that different molecular species might be responsible for emitting green or blue-green light. While C2 is the most frequent cause of such colors, other molecules can fluoresce at similar wavelengths. The challenge lies in identifying which ones, as they must be plausible constituents of a comet's environment and capable of responding to solar ultraviolet radiation in the appropriate manner. This is where cyanogen emerges in the narrative. Not to be confused with the deadly poison from fictional detective stories, though chemically related, cyanogen, CN, is a molecular radical composed of carbon and nitrogen. It is a commonly found substance in comets. When CN molecules absorb ultraviolet light, they can re-emit it in the violet and blue portions of the spectrum. Analysis of the same data that indicated unusual nickel production also noted that cyanogen generation from Comet Atlas was increasing dramatically as it journeyed closer to the Sun. This rate of increase followed a power law, escalating with heliocentric distance raised to the power of 9.38. This represents an exceptionally steep dependency, far exceeding that of typical comets. Could cyanogen be the source of the comet's green hue? It's plausible. CN emission bands can indeed extend into the blue-green wavelengths under specific circumstances. If CN was present in unusually high concentrations, and if factors like dust scattering were contributing to the perceived color, the combined effect might produce the observed green coloration without necessitating substantial amounts of C2. However, this explanation implies that Comet Atlas possesses a highly peculiar chemical composition, not only depleted in carbon chains, but also simultaneously enriched in nitrogen-containing molecules like CN. The question arises, why would an interstellar comet exhibit such a specific combination of characteristics? What processes during its formation or its billions of years traversing the galaxy would lead to such an unbalanced composition? Natural comets originating from our solar system display varying compositions influenced by their formation location. Comets originating from the Oort cloud, the vast spherical reservoir of icy bodies encircling our solar system, generally possess different ratios of volatile substances compared to comets from the Kuiper belt, the flattened disk of celestial objects beyond Neptune. These compositional differences are linked to factors such as formation temperature, the extent of processing by solar radiation, and whether they have previously made passes near the Sun. However, Comet Atlas did not originate within our solar system. It formed elsewhere, around a different star, under conditions we can only infer. It's possible its home system had distinct elemental abundances. Stars coalesce from clouds of gas that are not perfectly uniform in composition. Certain regions of the galaxy are richer in particular elements than others, a consequence of the history of supernova explosions that have enriched those areas. A star that forms in an environment abundant in nitrogen might produce comets with unusual ratios of nitrogen to carbon. Alternatively, Comet Atlas could be exceptionally ancient. Estimates based on its velocity and trajectory suggest an age ranging from 7 to 14 billion years, potentially twice the age of our Sun. If it is indeed that ancient, it would have formed during a period astronomers refer to as cosmic noon, when star formation within the Milky Way was at its zenith. The conditions during that era were different. More frequent supernova events, heightened radiation levels, and denser stellar environments. Perhaps comets formed during that epoch inherently possessed different compositions than those forming today. These are reasonable conjectures, grounded in astrophysics and our comprehension of stellar evolution and galactic history. They allow for Comet Atlas to be considered a natural celestial body while still acknowledging its profoundly anomalous characteristics. Yet, a competing idea persists, one that is difficult to dismiss. If one were tasked with designing a craft for interstellar travel, what would be utilized for propulsion? Chemical rockets are inadequate for the vast distances involved in interstellar journeys. Something more extraordinary would be required, such as ion drives that expel particles at extremely high velocities. Or, employing ingenuity, solar energy could be harnessed when approaching stars, causing volatile materials to sublimate and generate thrust, effectively using the star's own radiation to power trajectory adjustments. To disguise such a probe as a comet to any potential observers, it could be coated with ices and volatiles designed to sublimate predictably as it neared a star. Carbon dioxide ice would be a logical choice, stable at very low temperatures, abundant in space, and readily sublimates when heated. For controlled thrust during minor course corrections, the regulated sublimation of CO2 from specific outlets could be employed. Furthermore, if the probe utilized nitrogen-based propellants or coolants, any leaks or intentional releases might produce cyanogen as these substances interacted with solar radiation. This, of course, is speculative. It is crucial to emphasize that there is no direct evidence to suggest Comet Atlas is artificial. However, its chemical peculiarities, the depletion of carbon chains coupled with vigorous cyanogen production, the appearance of green coloration devoid of the anticipated molecules, collectively form a pattern that resists easy categorization within standard cometary models. One astronomer, speaking anonymously to a science journalist, remarked that if one were to compile a list of all observations pertaining to Comet Atlas and assess how many could be readily explained by natural cometary processes, the answer would be mixed. Some aspects align with natural phenomena. Active comets do release gases and form comas, and they can exhibit unexpected chemistry. However, when considering the entirety of the observed data, the cumulative probability of all these anomalies manifesting in a single natural object begins to feel disconcertingly low. This presents a Bayesian problem. Each individual anomaly, while perhaps improbable, might be possible. A green color with minimal C2, rare, but perhaps attributable to CN or another substance. Nickel without iron, bizarre, but potentially due to an exotic chemical reaction. A dominance of carbon dioxide, unusual for familiar comets, but not impossible for an object from another solar system. An elongated shape could be an artifact of imaging or a genuinely uncommon geometry. But when these probabilities are multiplied together, if each anomaly has a mere 10% chance of occurring naturally and 7 independent anomalies are observed, the combined probability becomes 0.1 raised to the 7th power, which equates to 1 in 10 million. It is important to note that the anomalies may not be entirely independent. Some could be interconnected, sharing common underlying causes, and the individual probabilities are largely estimations. We simply do not have sufficient data on interstellar objects to calculate precise statistics. Nevertheless, this exercise illustrates why some scientists began to feel that explaining every characteristic of Comet Atlas through natural phenomena required stretching the bounds of plausibility, not breaking them, but extending them to their limit. The verdant glow gradually diminished over subsequent weeks as Comet Atlas drew nearer to the Sun, eventually vanishing from Earth's view behind the solar glare. By the end of September, ground-based observations became impossible. The object's proximity to the Sun's position in the sky rendered it lost within the overwhelming brightness. It would remain unobservable from Earth until early December, at which point it would re-emerge on the opposite side of the Sun, having completed its closest approach to the Sun, perihelion. Consequently, the flyby by the Mars probe on October 3rd represented one of the final opportunities to study Comet Atlas before it reached its most active phase near perihelion. When the data from these observations remained unpublished and the silence from space agencies persisted, the enigmatic green mystery became yet another piece in a puzzle that refused to coalesce into a coherent picture. What exactly was Comet Atlas? Was it a naturally occurring comet with peculiar chemistry and an unlikely yet possible combination of traits? Or was it an object that merely resembled a comet while being fundamentally different? The answer, many surmised, lay in the increasingly prominent metallic signature, the production of nickel that defied simple explanations, and perhaps most unsettling, the pattern of how that nickel was being released, suggesting activation rather than passive sublimation. Chapter 5. Industrial Alloys from Deep Space. The Very Large Telescope, situated in Chile, is not a singular apparatus, but an intricate array comprising 4 colossal telescopes, each equipped with a primary mirror measuring 8.2 meters in diameter. When their capabilities are combined through interferometry, they can achieve a resolution equivalent to that of a telescope with a diameter exceeding 100 meters. This facility stands as one of the world's most powerful ground-based observatories, operated by the European Southern Observatory, and it has been actively observing Comet Atlas since July. The UVES spectrograph, which stands for Ultraviolet and Visual Echelle Spectrograph, is particularly adept at detecting faint emission lines emanating from metals. When atoms of elements such as iron, nickel, sodium, or calcium are present in a comet's coma and are energized by solar ultraviolet radiation, they emit light at very precise wavelengths. These emission lines serve as unique identifiers, akin to fingerprints. Each element produces a distinctive pattern, and the intensity of these lines reveals the quantity of that element being released. The team monitoring Comet Atlas with UVES included Rohan Rahat Gaon and his colleagues. Their primary objective was to detect metal emissions, as prior observations of comets had indicated that detecting metals was feasible but technically demanding. The temperatures within most comets are generally too low to vaporize the minerals that contain these elements. Typically, temperatures exceeding 1,000 Kelvin are required to sublimate silicate or metallic grains. Most comets, even those exhibiting significant activity, do not reach these thermal thresholds until they are exceptionally close to the Sun. However, Comet Atlas was exhibiting metal emissions even when it was situated beyond 3 astronomical units from the Sun, a distance 3 times farther from the Sun than Earth is. At such a distance, solar heating is considerably diminished. The intensity of sunlight decreases with the square of the distance. Being 3 times farther away means receiving 9 times less solar energy per square meter. Consequently, it should be far too cold for metals to sublimate. Yet, there they were, nickel emission lines, clear and undeniably present. Furthermore, as Comet Atlas journeyed closer to the Sun, these lines did not merely brighten incrementally, they intensified dramatically. Between late July and late August, a period during which the comet traversed a distance change from approximately 3.9 AU to 3.1 AU, the nickel production rate surged by a factor of 25, a 25-fold increase in nickel output per second within a single month. The research team modeled this increase and determined that it adhered to a power law. The production rate scaled with heliocentric distance raised to the power of 8.43, with a margin of error of plus or minus 0.79. This signifies an extraordinarily steep relationship. For comparative purposes, most cometary emissions scale with distance raised to a power between -2 and -4. Water sublimation, for instance, typically follows an inverse square relationship, -2, because it is driven by solar heating, which itself follows an inverse square law. A power of 8.4 indicates that the production rate is exquisitely sensitive to distance. Moving even slightly closer to the Sun results in a dramatic surge in the emission rate. This is not a gradual increase, it is explosive. Such a pattern deviates significantly from simple thermal sublimation of surface ices. Adding to the enigma is the iron situation, or rather, the lack thereof. The same observations that detected nickel emissions also searched for iron emission lines. Iron should logically be present. In every meteorite, every asteroid, and every sample of cosmic material ever analyzed, nickel and iron are invariably found together. While the specific ratio can vary slightly, depending on the mineral composition, they are consistently present in tandem. In the early observations of Comet Atlas, iron was not detected at all. Only as the comet approached closer and the nickel signal intensified did iron finally appear, and this occurred solely when Comet Atlas was within 2.64 AU of the Sun. Even then, the nickel-to-iron ratio was extreme, far exceeding that observed in any solar system comet or the previously detected interstellar comet, Borisov. The authors of the study described this finding as extremely puzzling. This phrasing represents a significant understatement in scientific literature. When researchers employ terms like extremely puzzling or unprecedented in peer-reviewed publications, it signals that they have exhausted conventional explanations and are venturing into territory where novel physics or chemistry may be required. Why would nickel be separating from iron? In terrestrial industry, we possess well-established methods for achieving precisely this. The Mond process, developed in the 1890s, utilizes carbon monoxide to form nickel carbonyl, a volatile compound that can be separated from iron-rich ores. This process involves heating the ore with carbon monoxide at moderate temperatures. Nickel reacts to form nickel carbonyl gas, which boils at 43 degrees Celsius. This gas is then collected and subsequently heated to higher temperatures, causing it to decompose back into pure nickel metal and carbon monoxide. The carbon monoxide is then recycled. The result is refined nickel. This is the method employed to produce high-purity nickel for electronic components, corrosion-resistant alloys, and the nickel plating used to protect steel parts. It is an industrial chemistry technique perfected over more than a century, a standard practice taught in metallurgy textbooks, and it appears to be occurring on Comet Atlas. Perhaps a natural explanation necessitates invoking the formation of nickel carbonyl through processes previously unobserved in comets. If the comet contains nickel-bearing minerals and carbon monoxide, the latter of which we know is present in abundance, then solar heating could potentially drive reactions that produce nickel carbonyl. This compound is sufficiently volatile to sublimate at relatively low temperatures, significantly lower than those required to vaporize metallic nickel or nickel silicates. Iron, conversely, might remain bound within different minerals that do not form analogous volatile compounds under the same conditions. While iron carbonyl does exist, its formation requires distinct conditions. If Comet Atlas possesses a very specific mineralogical composition, with nickel preferentially available in forms that can react with CO, while iron is locked within more stable compounds, then theoretically, the observed separation could occur. However, this scenario involves numerous assumptions. It presupposes a highly specific mineralogical makeup, unlike anything observed in solar system comets. It requires conditions that favor the formation of nickel carbonyl while suppressing iron carbonyl. Furthermore, it implies that these exotic conditions are sufficiently common for an interstellar comet to naturally exhibit them, despite interstellar comets being incredibly rare, this being only the third one detected. The alternative hypothesis is that the nickel signature originates not from natural sublimation, but from a manufactured surface. Nickel is extensively utilized in the construction of spacecraft. Nickel alloys are preferred for components subjected to radiation, extreme temperatures, and corrosive environments. Fuel tanks are frequently nickel-plated. Structural elements in satellites often employ nickel steel or nickel titanium alloys. Even spacecraft designed for planetary landings, such as the Mars rovers, incorporate nickel in their wheel mechanisms, joints, and electronic shielding. If Comet Atlas were artificial, possessing a metallic hull or structural framework, then as it approached the Sun, solar heating would cause surface materials to outgas. Coatings would vaporize. Any volatile compounds on the surface, including those used for thermal regulation or as protective layers, would sublimate. If the structure incorporated nickel-rich alloys, a logical choice for an interstellar probe requiring durability and radiation resistance, then nickel emissions would be anticipated. Furthermore, these emissions would be expected to follow a steep power law if the release was driven by a threshold effect. Imagine a probe covered by a layer of insulating material, perhaps accumulated over billions of years in interstellar space. As solar heating intensifies, the outermost layers would sublimate first, but the underlying metallic structure would remain shielded. Then, at a certain temperature threshold, the insulation layer would become thin enough for heat to reach the metallic surface. Once this occurs, the metal itself would heat rapidly, and any volatile compounds associated with it would begin to vaporize. This transition would be abrupt. Minimal emission below the threshold, followed by a rapid increase in emission as more of the metallic surface is exposed and heats up. The steep power law relationship would naturally emerge from such a threshold-activated process. Is this what is happening? It is impossible to ascertain without more data, but the observed pattern is consistent with activation rather than passive thermal sublimation. It appears as though something is switching on, rather than gradually warming up. Other metals were also sought in the spectroscopic data. Sodium, which is commonly found in many solar system comets and produces bright yellow emission lines, was not detected in significant amounts. Calcium, another metal sometimes observed in comets, was also absent. It was specifically nickel, with its characteristic green emission lines, that dominated the metallic signature. The temperature puzzle deepened when researchers calculated the surface temperatures required to account for the observations. Even at a distance of 2.1 AU, Comet Atlas should have a surface temperature of only around 200 Kelvin, far below the approximately 1000 Kelvin needed to sublimate silicate minerals. Yet nickel was being released efficiently. This implies either that the comet's surface was significantly hotter than simple thermal models predicted, perhaps due to an unusual greenhouse effect or an internal heat source, or that the nickel was not derived from direct mineral sublimation, but from an alternative process. The formation of nickel carbonyl would be consistent with lower temperatures, which is why it is the favored natural explanation. However, its formation requires the appropriate chemical environment, specific minerals, and precise reactant ratios. And there is one more detail that garnered attention. The cyanogen production followed an even steeper power law than the nickel. The CN emission rate scaled with distance to the power of 9.38. If natural chemistry is invoked to explain both the nickel and the cyanide, then whatever process is occurring must be capable of producing both in rapidly increasing quantities, with slightly different but consistently steep dependencies on solar distance. Cyanogen, in most of its forms, is toxic to terrestrial life. Hydrogen cyanide, HCN, is used in chemical warfare and executions, but the cyanogen radical, CN, is different. It is commonly found in comets, formed from ammonia or other nitrogen-bearing molecules when they are dissociated by ultraviolet light. Discovering CN in a comet is not surprising. However, finding it at the observed production rates with such a steep distance dependence is noteworthy. Consider the nickel and the cyanogen together. Both are increasing steeply. Both follow power laws, suggesting threshold effects or activation rather than simple thermal sublimation, and both defy easy explanation through conventional cometary chemistry. Interestingly, both are molecules with industrial or technological relevance: nickel in alloys and plating, and cyanide compounds in chemical synthesis and materials processing. Is this mere coincidence? Are we witnessing natural processes that coincidentally mimic what we would expect from technology? Were we instead observing indicators that were manufactured intentionally designed and intended for purposes exceeding mere natural atmospheric release. The gathered data could not definitively resolve this query, yet it bolstered the growing sentiment that 3 Atlas was unlike any celestial body humanity had previously encountered. With its closest approach to the Sun, known as perihelion, slated for October 29th, when the comet would be a mere 1 3600th astronomical units from our star, the emission of metallic elements would reach their zenith. Should these observed trends persist, and the established power laws continue to their logical culmination, the production of nickel would escalate by several additional orders of magnitude in the ensuing weeks. That precise juncture, marked by peak solar heating, most vigorous outgassing, and the vaporization of any surface constituents under immense thermal duress, would serve as the ultimate test. Would 3 Atlas behave as a comet pushed beyond its inherent limits, potentially fracturing or erupting spectacularly? Or would its behavior suggest something engineered, perhaps harnessing solar energy for propulsion or trajectory adjustments for reasons beyond our current comprehension? The metallic signature provided a critical piece of the puzzle. However, much like all other clues in this peculiar enigma, it pointed in multiple directions simultaneously, evading definitive interpretation. And while scientific minds grappled with the dichotomy of nickel carbonyl versus manufactured alloys, another set of anomalies began to demand attention. The very trajectory, the path that 3I Atlas was tracing through our solar system, exhibited its own distinctive irregularities, mathematical improbabilities that stretched the very fabric of coincidence. Chapter 6. 7. Improbable events preceding perihelion. Avi Loeb has emerged as a figure of considerable division within astronomical circles. To his proponents, he represents a rare breed of scientist, unafraid to question established dogma, to pose challenging inquiries, and to explore avenues that others readily dismiss. To his detractors, he is too quick to resort to extraordinary explanations when simpler ones might suffice. He is perceived as excessively eager for media spotlight and too willing to disseminate provocative hypotheses before they have undergone rigorous peer review. Nevertheless, his academic pedigree is unimpeachable. Former chairman of Harvard's astronomy department, founding director of the Black Hole Initiative, author of over 800 published works, and recipient of accolades from institutions worldwide. When he addresses astrophysical matters, his pronouncements command attention, even from those who hold dissenting views. In early October, on the very day 3 Atlas made its closest passage to Mars, Loeb disseminated a compilation of what he termed the 7 peculiar characteristics of this interstellar visitor. While some of these have already been alluded to, comprehending them as a cohesive set, observing their interconnectedness and compounding effect, truly reveals the profound depth of the mystery. The initial anomaly pertained to the object's scale and mass. Upon the discovery of 3 Atlas in July, astronomers calculated its brightness and extrapolated backward to estimate its size. Assuming the object reflects approximately 5% of incident sunlight, a typical albedo for asteroids and cometary nuclei, its observed luminosity from Earth suggested a diameter of approximately 20 kilometers. A 20-kilometer object is exceptionally large for an interstellar visitor. Oumuamua, the first confirmed interstellar object, was estimated to be around 100 meters in diameter, roughly the length of a football field. 2I Borisov, the second interstellar visitor, measured approximately 1 kilometer in diameter. Here, 3 Atlas presented the potential for a size 20 times greater than Borisov and 200 times larger than Oumuamua. The fundamental issue with such substantial interstellar bodies is their extreme rarity. planetary systems do not readily dislodge their largest components. During planetary formation, gravitational interactions scatter objects outwards, with smaller bodies being more susceptible to ejection. The greater the mass of an object, the stronger its gravitational bond to its home system, making escape velocity more difficult to attain. The expectation is that interstellar space would primarily be populated by minuscule debris, with progressively larger objects becoming exponentially scarcer. Loeb's calculations indicated that if 3 Atlas were indeed 20 kilometers in diameter, its detection within 5 years of continuous sky surveys would necessitate a supply of interstellar objects on a scale that is simply untenable. The Milky Way would have to be generating and expelling objects of this magnitude at rates far exceeding those predicted by models of stellar and planetary system formation. This would imply that nearly every star system ejects substantial planetary remnants, a scenario that fundamentally contradicts our current understanding of celestial dynamics. The alternative hypothesis posits that the object is not 20 kilometers of solid rock. Rather, the majority of its observed brightness stems from an extensive envelope of dust and gas, with a significantly smaller nucleus concealed within. This explanation would be consistent with a comet, thus reducing its mass to more plausible levels. However, this then necessitates an explanation for why this comet exhibits all the other anomalous characteristics. Its extraordinarily peculiar chemical composition and its production of metals at seemingly impossible rates. The second peculiarity involves the sunward jet. When the Hubble Space Telescope captured images of 3 Atlas on July 21st, the photographs revealed an unusual phenomenon. Scattered sunlight appeared to extend in the direction of the sun rather than away from it. Comets typically develop tails that point away from the sun due to the outward push of solar radiation pressure and solar wind on gas and dust. The tail consistently points in an anti-solar direction, akin to a windsock indicating the direction of the solar wind. However, 3 Atlas displayed the inverse, a luminous extension towards the sun, what astronomers refer to as an anti-tail. Loeb and his colleague Eric Keto meticulously analyzed the Hubble imagery and concluded that the glow extended approximately 10 times farther towards the sun than it did in perpendicular or outward directions. When factoring in the viewing geometry, the angle from which Hubble was observing, this 10-to-1 ratio becomes even more pronounced. Anti-tails are not entirely unprecedented. Certain comets exhibit them due to specific geometrical effects, where dust particles released earlier in their orbits remain within the comet's orbital plane and appear to point forward when viewed from particular angles. However, these are typically transient, appearing and vanishing as the viewing geometry shifts, and they do not usually demonstrate the extreme elongation ratio observed with 3 Atlas. A sunward jet could signify active venting from the sunward face of the nucleus. If volatile substances are sublimating preferentially from the hemisphere oriented towards the sun and expelled with sufficient velocity to momentarily overcome radiation pressure, a plume directed sunward could materialize. Yet, this requires exceptionally precise conditions and highly vigorous outgassing. Furthermore, it still fails to account for the extreme elongation or the persistence of the feature across multiple observations. The third, fourth, fifth, and sixth anomalies are all intrinsically linked to the trajectory, and it is here that statistical improbability becomes particularly striking. 3 Atlas entered our solar system on a retrograde orbit, traveling in the opposite direction to the orbital motion of the planets. Its orbital plane is inclined by approximately 5 degrees relative to the ecliptic, the plane in which Earth and most other planets revolve. While 5 degrees may seem minor, space is a 3-dimensional realm. If interstellar objects arrive from random directions, as they logically should, given the absence of any preferential approach vector, then the probability of an orbit falling within 5 degrees of the ecliptic plane is approximately the solid angle of that zone divided by the total solid angle of a sphere. This calculation yields roughly 0.2%, or 1 in 500. While not impossible, it is statistically unlikely. If 3 Atlas arrived randomly, one would anticipate its appearance from any direction with equal probability. The ecliptic plane holds particular significance for our solar system due to the presence of the planets, but it possesses no inherent importance in the vastness of interstellar space. Therefore, the alignment of this interstellar visitor with this plane warrants scrutiny. Furthermore, consider the close encounters. 3 Atlas passed within 29 million kilometers of Mars on October 3rd. It is projected to approach Venus closely, and its trajectory will bring it relatively near Jupiter in March of 2026. These are not direct impacts or even exceptionally close flybys by cosmic standards, but they represent closer proximity than one would statistically anticipate for an object following a random trajectory. Loeb calculated the probability that an interstellar object entering the solar system on a random trajectory would happen to pass in proximity to multiple planets. The answer is contingent upon the definition of proximity. However, employing reasonable parameters for close approach distances, the cumulative probability emerges at approximately 0.005%, or 1 in 20,000. Again, not an impossibility. Improbable events do occur. Lottery winners exist despite odds measured in the millions to 1. However, one begins to question when an accumulation of improbable occurrences comes to light. The timing of these events is also a crucial factor. Planets orbit at varying speeds. Mars requires approximately 687 days to complete a single revolution. Jupiter takes nearly 12 years. Venus completes its orbit in 225 days. The probability that an interstellar object arrives not only on a trajectory that facilitates close proximity to 3 planets, but also at a time when each planet is positioned appropriately in its orbit for such an encounter, represents a multiplication of the already low trajectory probability by an additional factor. Loeb's approximate estimate for the combined probability of both trajectory alignment and opportune timing stands at roughly 1 in 200,000. This scenario involves the superposition of improbable events. The 7th anomaly is perhaps the most speculative, yet undeniably the most captivating. When traced backward into interstellar space, the direction from which 3 Atlas originated corresponds to a region of the sky near Sagittarius. This in itself is not surprising, as Sagittarius is oriented towards the galactic center, a star-rich expanse. However, Loeb noted that this direction lies within 9 degrees of another renowned signal emanating from that general vicinity. On August 15, 1977, the Big Ear radio telescope in Ohio detected a potent, narrow-band radio signal that persisted for 72 seconds. The signal occurred precisely at the frequency at which neutral hydrogen naturally emits, a frequency that many SETI researchers posit as an optimal choice for interstellar communication, as any technologically advanced civilization would likely be aware of it. The signal's exceptional nature and apparent artificiality prompted astronomer Jerry Amon to famously annotate it with "WOW" on the computer printout. It subsequently became known as the WOW signal. Despite numerous attempts, the signal has never been detected again. Explanations range from terrestrial interference to a transient comet that coincidentally generated a signal at the precise frequency to, indeed, an extraterrestrial transmission. The mystery remains unresolved nearly 50 years later. Is it significant that the trajectory of 3I Atlas, when extrapolated backward, points to a location within 9 degrees of the origin of the WOW signal. Loeb calculated the probability of this alignment at approximately 0.6%. While the odds are more favorable than some of the other coincidences, it remains an unlikely occurrence. However, consider this. If an extraterrestrial civilization were to dispatch a probe to a solar system they had identified, perhaps through radio transmissions or by observing planetary transits, how might they herald their arrival? They might first transmit a radio signal, a message of greeting, signaling their awareness. Subsequently, if they intended to send a physical probe, they might direct it along the same trajectory from the same originating point, enabling anyone connecting the dots to ascertain a relationship between the signal and the probe. This is, of course, speculative. Linking 3 Atlas to the WOW signal necessitates the assumption that both are artificial and interconnected, a considerable leap beyond what the current data conclusively supports. Nevertheless, the alignment is demonstrable and documented, adding yet another layer to a picture already replete with improbabilities. When enumerated, these 7 anomalies collectively exert a substantial weight. The unusually large size for an interstellar object, the jet that contradicts typical cometary behavior, the extreme chemical composition characterized by the presence of nickel without iron and a predominance of carbon dioxide, the green coloration devoid of the requisite molecular signatures, the trajectory aligned with the ecliptic plane, the timing of arrival optimized for planetary close approaches, and the direction of arrival coinciding with a historically anomalous radio signal. Each of these anomalies possesses plausible natural explanations. In some instances, these explanations require significant stretching or invoke specific, unusual circumstances or rely on poorly understood chemical processes. However, they remain naturalistic explanations. Science operates by seeking natural explanations for observed phenomena. It is only when natural explanations become more convoluted and less probable than artificial ones that the consideration of the latter becomes imperative. This threshold is subjective, influenced by one's preconceived notions regarding the likelihood of artificial origins. If one holds that the probability of encountering alien technology within our solar system is virtually zero, then no quantity of anomalies will sway this conviction. Even highly improbable natural explanations will be favored, as they are still perceived as more likely than extraterrestrial involvement. Conversely, if one entertains even a minimal prior probability that interstellar probes could exist and occasionally traverse our solar system, then each anomaly serves to incrementally adjust that probability upward. As multiple anomalies accumulate, what began as an exceedingly small probability becomes less negligible. It may remain improbable, but it ceases to be dismissible. Loeb has been explicit in his assertions. He has repeatedly stated that 3 Atlas is most likely a natural comet. However, he contends, and herein lies the crux of the controversy, that the possibility of it being artificial warrants serious investigation. He advocates for the collection of maximum possible data, the deployment of our most sophisticated instruments, the targeting of radio telescopes towards it, the meticulous analysis of every spectrum, and the tracking of any deviations from purely gravitational motion. His reasoning is that even a 1%, or even 0.1% chance that we are observing a probe from another civilization carries implications so profound that a thorough investigation becomes a moral imperative. The cost of error is minimal. We observe an unusual comet and gain insights into interstellar chemistry. The cost of negligence, should it be artificial, is the missed opportunity of first contact. This line of reasoning divides the scientific community. Some perceive it as prudent caution and an open-minded scientific inquiry. Others view it as sensationalism, a lowering of evidentiary standards in pursuit of improbable scenarios. The debate underscores deeper questions concerning how science should approach truly anomalous observations, how to strike a balance between skepticism and curiosity, and how to determine when an observation is sufficiently peculiar to merit exceptional attention. All of these considerations, the 7 anomalies and the ongoing discourse surrounding their implications, were poised to culminate at a critical juncture on October 29th, when 3 Atlas reached perihelion and confronted the full intensity of solar radiation at its closest solar proximity. Chapter 7. What the Politicians Comprehend. A peculiar protocol is in place within the corridors of power in Washington. When scientific matters intersect with concerns of national security, information transits through channels unseen by the public eye. Intelligence briefings are conducted behind closed doors. Congressional committees possessing security clearances receive updates that are not disseminated through public announcements. Occasionally, carefully chosen phrasing in public statements reveals that individuals in positions of authority possess more knowledge than they openly disclose. Queries regarding the object began to surface on October 2nd, the day preceding 3 Atlas's closest approach to Mars. Stephen Miller, serving as Deputy Chief of Staff for Policy at the White House, was making appearances on news programs to discuss the ongoing government shutdown. These were routine engagements, focused on budget negotiations and operational continuity. However, during one particular program, a journalist posed a question that appeared to momentarily disconcert Miller. Had the president been briefed on 3 Atlas? Miller's response was measured and deliberate. He confirmed that relevant agencies were actively monitoring the situation. He offered assurances regarding the competence and thoroughness of scientific oversight. He emphasized that there was no imminent danger to Earth, and that the object would pass at a considerable distance from our planet. Yet, he conspicuously avoided directly answering whether the president had received a briefing. He neither confirmed nor denied the premise. Instead, he pivoted to discussing the capabilities of American space programs and the imperative of sustained investment in NASA. This non-response was, in itself, revealing. If 3 Atlas were merely an object of astronomical interest, a natural comet passing through, the expected reply would have been straightforward. No, the president has not been briefed on individual astronomical observations. Thousands of astronomers make discoveries daily. Presidential briefings are reserved for matters of national significance, security threats, and diplomatic crises. A comet, however unusual, would not typically warrant such attention. However, Miller did not offer this dismissal. He did not treat the question as absurd. Instead, he acknowledged it with gravity, spoke of ongoing surveillance, and employed language that suggested sustained attention from federal entities. This choice of articulation, this reluctance to simply negate the premise, implied that 3 Atlas had indeed reached a level of government where decisions regarding information management were being actively made. Concurrently, Representative Tim Burchett from Tennessee appeared on Newsmax. Burchett sits on the House Oversight Committee, an entity with jurisdiction over federal agencies, including NASA. He has been a vocal advocate for transparency, particularly concerning unidentified aerial phenomena, championing the declassification of government records and the public disclosure of information held by agencies regarding unexplained objects. Burchett appeared on screen alongside Avi Loeb, both individuals discussing 3 Atlas and its associated anomalies. The joint appearance itself was noteworthy. Congressional representatives do not typically share airtime with astrophysicists to deliberate on ongoing scientific observations. Their interviews typically focus on legislation, policy, or political controversies. Science communication is generally relegated to scientists and educators. Yet, here was a member of Congress, during an active government shutdown, allocating time to publicly discuss an interstellar object. Burchett articulated the necessity of transparency and ensuring public access to data collected by federally funded missions. He framed it as a matter of principle, asserting that NASA's observational data rightfully belongs to the American people who funded it. He posited that there was no justification for withholding observations of a natural phenomenon. The underlying message was unmistakable. Burchett harbored the belief that information was being withheld, and he was leveraging his public platform to exert pressure, making it politically inconvenient for agencies to remain silent. Subsequently, Representative Marjorie Taylor Greene from Florida entered the discourse. Greene had apparently been briefed on the elongated Perseverance images. She directly contacted Avi Loeb, soliciting his analysis of the photograph depicting the anomaly. This action is unusual. Members of Congress routinely receive scientific briefings, but these typically originate from agency officials, NASA scientists, or designated experts from the Science and Technology Committee. They do not typically initiate unsolicited calls to university professors for second opinions. The fact that Greene sought external expert analysis suggests either dissatisfaction with official explanations or a complete absence of official explanations. Either scenario is cause for concern. If NASA provided briefings that failed to adequately elucidate the images, it implies uncertainty or evasiveness on the part of the agency itself. If NASA failed to provide any briefings despite congressional interest, it indicates that information was actively being suppressed. Greene took her advocacy a step further. She dispatched a letter to NASA's leadership urging the utilization of the Juno spacecraft, currently in orbit around Jupiter, to study 3 Atlas when the comet approaches Jupiter in proximity in March of 2026. The letter underscored the scientific merit, the exceptional opportunity, and the significance of maximizing observations of interstellar objects given their rarity. However, correspondence from representatives to agency heads concerning specific scientific missions is not standard procedure. While Congress establishes budgets and provides oversight, it generally does not engage in micromanagement regarding which astronomical targets specific spacecraft should investigate. These are matters left to mission scientists and panels tasked with peer review. Luna's communication indicated either extraordinary public fascination, which seems improbable for a minor celestial occurrence, or significant apprehension stemming from information so compelling that she felt compelled to directly influence mission planning. The consistent theme across these governmental interactions suggested a deeper reason. Multiple members of Congress from various committees showing interest in 3 Atlas, White House personnel being questioned about presidential updates, and scientists being invited to share speaking platforms with political figures. Such attention is not typical for routine astronomical discoveries, regardless of their scientific merit. Consider the precedent. When the initial photograph of a black hole was unveiled in 2019 by the Event Horizon Telescope collaboration, it commanded front-page coverage, a scientific landmark representing the culmination of decades of theoretical groundwork and years of data analysis. Yet, no members of Congress appeared on television to discuss it, nor did the White House issue statements. It remained a scientific narrative, reported by science journalists and celebrated by the astronomical community, without being elevated to the level of political discussion. Alternatively, recall the discovery of phosphine in Venus's atmosphere in 2020, which momentarily raised the possibility of microbial life within the Venusian clouds. In some respects, this was a more significant story, touching upon astrobiology and the quest for extraterrestrial life. It sparked enthusiasm and debate, but again, involved no political engagement beyond standard NASA press releases. 3 Atlas presented a different scenario, and its distinction seemed to lie precisely in its ambiguity, its unanswered questions, and the potential for evolving interpretations based on the actual data. There is a relevant historical context to consider. In 1960, when the earliest serious proposals for SETI, the search for extraterrestrial intelligence, emerged, scientists and policymakers discreetly established protocols for handling the detection of an artificial signal. These protocols prioritized verification, prudence, and international collaboration before any public announcement. The underlying assumption was that a unilateral revelation by a single nation or organization could incite panic, be misconstrued, or provoke diplomatic disputes. While these protocols are not legally binding treaties, they represent guidelines formulated through workshops and conferences, offering recommendations for best practices. They reflect a consensus that the detection of intelligence would be an event impacting the entire species, with ramifications extending beyond scientific inquiry, necessitating coordination at governmental levels. If the observations of 3 Atlas yielded data ambiguous enough to potentially indicate artificial origins, even as a solitary possibility among many, it would be logical for federal agencies to inform elected officials. The purpose would not be to confirm alien technology, but to apprise them of an anomalous situation where public interest was high and data interpretation remained uncertain, thereby preparing them for constituent and media inquiries and ensuring coordinated messaging to prevent interagency contradictions. The government shutdown complicated matters considerably. Under normal circumstances, NASA maintains public affairs officers, prepared statements, and coordinated communication strategies. However, during a shutdown with minimal staff, this infrastructure collapses. Scientists on furlough cannot address media inquiries, press releases go unwritten, and interagency coordination falters. Into this void, individual scientists began to communicate independently, with some publishing daily blog posts, others granting interviews to science journalists, and amateur researchers posting analyses on social media platforms. In the absence of centralized coordination, the narrative fragmented, with multiple interpretations circulating concurrently, none officially sanctioned, and all vying for attention. From a political standpoint, this presented a challenge. When managing information about an ambiguous situation, decentralized communication, where various experts offer conflicting interpretations, is highly problematic. It complicates governance, makes consistent messaging more difficult, and invites conspiracy theories by allowing speculation to flourish in the absence of official clarification. Some observers proposed that this timing was intentional, suggesting the shutdown was orchestrated to impede coordinated disclosure. They posited that by furloughing NASA staff, the administration created a plausible deniability for the lack of information release, framing the silence as a logistical consequence of scientists not working, data not being processed, and websites not being updated, rather than deliberate suppression. However, coincidences in timing can indeed be genuine. Government shutdowns occur when budget negotiations fail, driven by political factors entirely unrelated to celestial events. The fact that October first coincided with the Mars flyby just 2 days prior was purely by chance. The federal fiscal year concludes on September 30th, and the passage or failure of continuing budget resolutions hinges on congressional votes and presidential decisions regarding signing or vetoing. A comet's trajectory does not influence this legislative process. Nevertheless, the coincidence was unsettling, much like the accumulation of 7 anomalies in the trajectory and chemical composition of 3 Atlas, which began to feel less like random chance. The confluence of official silence, technological reticence from multiple nations, and a shutdown that disrupted communication precisely when it was most needed, all of it felt orchestrated, even if it wasn't. Dr. John Brandenburg, a plasma physicist with experience in defense research, added another voice to the political discourse. Brandenburg maintains a website called Blue Planet Red, where he discusses Mars research, including speculative theories regarding past nuclear events on the planet. He released a video analyzing 3 Atlas, referencing White House statements, and noting that official assurances often precede more detailed revelations. Brandenburg's professional history is mixed. He has authored peer-reviewed papers on plasma physics, alongside speculative theories about ancient Martian civilizations, which are largely dismissed by the scientific community. He occupies an ambiguous space where legitimate credentials coexist with fringe theories. However, his involvement underscored how 3 Atlas was attracting attention from diverse sources, ranging from mainstream scientists to individuals operating at the fringes of accepted knowledge. The evident political interest, the high-level inquiries, and the unusual coordination required to explain the silence across multiple nations all suggested that 3 Atlas had transcended its status as a mere astronomical curiosity. It had become an event necessitating management, demanding decisions about the timing and content of disclosures, and requiring briefings and coordination beyond the scope of typical scientific discoveries. And that careful control of information could not persist indefinitely. Eventually, observations would be analyzed, papers would be published, and data would enter the public domain through peer review or leaks. The questions would demand answers, and those answers, when they emerged, would need to address not only the nature of 3 Atlas, but also the reasons behind the involvement of political entities in its observation. In the interim, amateur astronomers were not awaiting official pronouncements. They possessed their own telescopes, their own processing software, and their own communities for sharing and analyzing data. In the absence of professional releases, amateur observations became the primary visual source of information regarding 3 Atlas. Some of these observations introduced new questions, with certain images appearing to depict anomalies, while others were almost certainly the result of imaging artifacts, misinterpretations, or wishful thinking. However, distinguishing genuine signals from noise when observing faint objects through Earth's atmosphere with modest equipment becomes nearly impossible without professional resources to establish a baseline of accuracy. Chapter 8. The Amateur Images. NASA doesn't want you to see. Amateur astronomy boasts a rich legacy of contributions to professional science, including the discovery of supernova, comets, and variable stars. These endeavors often rely on networks of amateur observers equipped with backyard telescopes and a dedication to skywatching. Worldwide, thousands of amateur astronomers possess equipment that, just a generation ago, would have been considered professional grade, including CCD cameras, computerized mounts, and sophisticated image processing software. The demarcation between amateur and professional capabilities has significantly blurred. Upon the discovery of 3 Atlas, amateur astronomers promptly commenced tracking it. Coordinates were disseminated online, and ephemerides, tables predicting the object's position each night, were calculated and shared. Observing campaigns were organized through forums and social media groups, driven by a collective desire to witness this interstellar visitor firsthand and capture photons that had reflected off an object from beyond our solar system. One such observer, operating under the username Dobsonian Power, a nod to the popular and aperture-efficient Dobsonian telescope design, was observing on October 3rd as 3 Atlas approached Mars. Dobsonian power utilized a solar telescope, a device engineered to safely observe the sun by blocking most of its light while permitting specific wavelengths to pass. The rationale for employing a solar telescope to observe a comet stemmed from 3 Atlas's position in the sky relative to the sun from Earth's vantage point. Though not directly in front of the sun, it was sufficiently close to necessitate daytime observation with specialized equipment. Solar telescopes equipped with narrowband filters can detect bright objects near the sun that would otherwise be obscured by solar glare, rendering them invisible to conventional telescopes. Dobsonian power captured an image and uploaded it online. The image underwent extensive processing, with contrast amplified to accentuate faint features. The resulting image was controversial, revealing a dark, somewhat elongated form against a lighter backdrop. Though grainy and indistinct, it undeniably suggested some form of structure. Within hours, the image went viral, sparking a deluge of interpretations in comment sections. Some interpreted it as definitive proof of an elongated object, corroborating the Perseverance images. Others dismissed it as mere noise, artifacts of aggressive image processing, or pareidolia, the human inclination to perceive patterns in random data. A few commentators pointed out that solar telescopes are not designed for comet observation and that their optics could introduce distortions. Professional astronomers were swift to voice their skepticism, citing the image's poor quality and excessive processing. Without precise details on equipment parameters, exposure times, and processing steps, evaluating the authenticity of the signal versus artifacts was deemed impossible. One astronomer remarked that with sufficient image enhancement, any object can be made to appear structured. Noise patterns can manifest as features, and optical aberrations can resemble edges, with the human brain subsequently connecting these elements into discernible shapes. Despite its technical limitations, the image's dissemination continued unabated. News outlets reported on it, YouTube videos offered analyses, and comparisons were drawn to the Perseverance images, earlier Hubble photographs, and artistic renditions of potential interstellar probes. Inevitably, AI-generated images began to surface, purportedly depicting the true appearance of 3 Atlas, sleek metallic constructs with impossible detail, entirely fabricated, but presented as enhanced versions or artistic interpretations. This proliferation of AI-generated content introduced a secondary challenge: distinguishing genuine, albeit flawed, amateur observations from fictional renderings designed to attract clicks. While some AI images were overtly fabricated, exhibiting surface details unresolvable by any telescope at such distances, others were more subtle, showcasing plausible comet-like structures with just enough ambiguity to appear as authentic photographs. Meanwhile, legitimate amateur observations persisted. Astrophotographers utilizing tracking mounts, telescopes that automatically compensate for Earth's rotation to maintain targets in view during extended exposures, captured images of superior quality compared to Dobsonian Power's solar telescope attempt. Gerald Raymond and Michael Jagger in Namibia had already documented the shift in color to green. Other observers in the southern hemisphere, where 3 Atlas was better positioned before its passage behind the sun, uploaded their findings to astronomy forums. These images revealed something noteworthy. When properly tracked and imaged using narrowband filters that isolated specific emission lines, 3 Atlas appeared to possess an elongated white or yellow core surrounded by a green halo. In many of the superior images, the core exhibited noticeable elongation, not dramatically so, but to a degree that made it distinctly non-circular. The elongation ratio was not the 4:1 observed in the Perseverance composite, but closer to 2:1 or 1.5:1. The question remained, was this genuine structure, or still an artifact? While tracking telescopes correct for Earth's rotation, the comet itself moves against the backdrop of stars. If exposure times are prolonged, this motion can cause image blurring, potentially leading to elongation in the direction of movement. However, some exposures were brief, under a minute, insufficient to cause significant smearing. Furthermore, the observed elongation appeared consistent across different observers, employing various equipment in different locations. One observer, identified as Dr. Horace Drew and posting under the name Red Collie, had been particularly vocal regarding the color distribution. Drew shared enhanced versions of multiple amateur images, illustrating the white center and green periphery. His central argument remained that if the object were a small spherical nucleus enveloped by a large green coma and observed through a telescope that introduced slight image smearing due to atmospheric turbulence and instrument limitations, one would expect to see a predominantly green blur. The dominance of white in the center, he contended, would only occur if the white emitting region surpassed the green emitting region in size. Professional astronomers countered that cometary comas are not uniformly bright. They are densest near the nucleus and diminish with distance. If a bright nucleus is surrounded by a fainter coma, even if that coma is green and extensive, the central brightness from the nucleus will dominate images unless exposures are specifically calibrated to reveal faint, extended emission. Most amateur images are optimized to capture the bright core, not the diffuse outer coma. Consequently, observing white centers is not unexpected. The back-and-forth exchange between Drew and other observers highlighted a fundamental challenge. Interpreting astronomical images necessitates a thorough understanding of the imaging process, instrument response, exposure settings, and applied processing techniques. Two individuals examining the same raw data can produce distinct processed images that emphasize different features. In the absence of established standards for image processing, debates regarding the actual content of images become subjective. Amateur images also suffered from a signal-to-noise ratio issue. 3 Atlas was never particularly bright, reaching a peak magnitude of around 8 or 9, too faint to be seen with the naked eye, but visible through binoculars or small telescopes under dark skies. Most amateur equipment possesses limited sensitivity, requiring long exposures, frame stacking, and careful processing to capture a clear image. Each of these steps introduces potential for artifacts. Professional observatories are equipped with larger mirrors, superior cameras, darker observing sights, and decades of experience in instrument calibration. They are familiar with their telescope's idiosyncrasies, possess methods for correcting optical aberrations, can flat field images to mitigate uneven detector sensitivity, and can subtract background sky glow. Amateur observers frequently lack this expertise or equipment. While their images are valuable for initial detection and broad characterization, they are less suitable for detailed analysis of subtle structural features. Nevertheless, in the absence of professional imagery from Mars orbiters, amateur observations represented the public's sole visual resource, creating a vacuum where speculation could flourish unchecked. Had NASA or ESA released even preliminary high-resolution images, even raw, uncalibrated frames, it would have grounded the discourse in empirical reality. The public could have debated the content of professional images, but at least that debate would have been rooted in high-quality data. Instead, the conversation revolved around heavily processed amateur images of varying quality, augmented by AI-generated fabrications disseminated through social media algorithms that prioritized engagement over accuracy. The most vocal contributors were not necessarily the most knowledgeable. The most sensational interpretations garnered the most shares, making the truth, whatever it might be, increasingly difficult to discern from the surrounding noise. Some observers attempted to inject reason into the discussion. They published tutorials on astrophotography, explaining common artifacts and demonstrating how processing choices influence final images. They illustrated the ease with which false structures could be created through over-sharpening, how cosmic ray impacts on camera sensors could resemble stars or anomalies, and how diffraction spikes from telescope supports might be mistaken for genuine features. However, nuance rarely achieves viral status. Careful explanations receive fewer views than bold assertions. And when individuals desire to believe in something extraordinary, they tend to selectively trust expert opinions, often viewing skeptical astronomers as participants in a cover-up and enthusiastic interpreters as truth-tellers. The inherent quality control mechanisms of science, such as peer review and replication, function poorly on social media platforms, where anyone can publish any content, and algorithms amplify whatever generates clicks. A website emerged dedicated to compiling and analyzing all available images of 3 Atlas. This site, managed by an individual identifying as an independent researcher, aggregated amateur observations, professional press releases, scientific papers, and blog posts. However, it accorded equal prominence to unsubstantiated speculation and rigorously vetted data. A graph illustrating nickel emission rates from the Very Large Telescope was presented alongside AI-generated images of hypothetical spacecraft. This conflation of reliable and unreliable sources fostered an environment where distinguishing truth from fiction required an expertise that most visitors lacked. As October progressed and 3 Atlas drew nearer to the Sun, Earth-based observations became unfeasible. The angular separation from the Sun diminished to a point where even specialized equipment could not safely observe. By mid-October, the comet was obscured by solar glare from our perspective. It would remain invisible until early December, when it would re-emerge on the far side of the Sun. By that time, its perihelion passage would have occurred, and its most intense activity would have subsided. Consequently, the amateur observation campaign concluded precisely when events were reaching their most compelling stage. The final images captured before solar conjunction depicted 3 Atlas intensifying, its coma expanding, and its green glow becoming more pronounced, all consistent with a comet approaching perihelion and exhibiting increased outgassing due to rising solar temperatures. Nothing in those concluding amateur images definitively resolved the disputes concerning its structural composition. They showed an active, bright, and fuzzy comet traversing the sky as anticipated. However, the cessation of Earth-based observations meant that whatever transpired at perihelion would be witnessed solely by spacecraft. The Solar and Heliospheric Observatory, SOHO, orbiting at the L1 Lagrange point between Earth and the Sun, possessed instruments capable of observing the region near the Sun. The Parker Solar Probe, during its close approaches to the Sun, might also have captured glimpses. The ESA's JUICE spacecraft, en route to Jupiter, held a strategic position beyond Earth's orbit, poised for crucial observations scheduled for November. These observations were vital, designed to capture 3-eyed Atlas at its peak activity. During this period, solar energy would be at its maximum, outgassing would reach its zenith, and any unusual behaviors would be most conspicuous. If the object was indeed capable of anomalous actions, be it fragmentation, evasive maneuvers, or any deviation from typical cometary physics, its perihelion passage was predicted to be the moment of revelation. October 29th loomed as the ultimate test. On this date, 3-eyed Atlas was slated to approach the Sun at a distance of 1.36 astronomical units, a point just within Mars' orbit, bringing it closer to our star than it had been in its billions of years journeying through interstellar void, and even closer than it likely experienced during its formation within its native star system. Assuming its home star was comparable to or cooler than our Sun, the immense influx of gigawatts of solar energy upon its surface posed a profound question. Would it withstand this onslaught intact, or would the thermal stresses fracture its nucleus into myriad fragments? Would the release of gases follow predictable patterns aligned with thermal models, or would the steep power law relationships governing nickel and cyanide production escalate to unprecedented rates? Would the object continue its hyperbolic trajectory unaltered, or would subtle, non-gravitational forces arising from asymmetric outgassing measurably deflect its course? Beneath these scientific inquiries lay a more profound, unspoken question that permeated every discussion, a notion few dared to voice too loudly. If three-eyed Atlas was not a natural phenomenon, if some of its peculiar characteristics hinted at artificial origins rather than geological processes, could its perihelion passage be a pre-programmed event, a moment of activation, a cosmic recharge for systems dormant for eons in the frigid expanse of space? Could an object perceived as a comet from afar, under intense solar illumination, reveal itself to be something entirely different? This realm of speculation proved unsettling for scientists, venturing into territories where data became sparse and the imagination rushed to fill the void. Yet October 29th was rapidly approaching, and when it arrived, keen eyes would undoubtedly be watching, somewhere. Chapter 9. October 29th, the apex of truth. Perihelion signifies more than a mere point in an orbit. It is a crucible. For comets, this juncture represents the peak of physical stress, the zenith of energy input, and the highest level of activity. The underlying physics is elegantly straightforward. Solar radiation intensity follows an inverse square law. At 1 astronomical unit from the Sun, equivalent to Earth's orbital distance, the solar constant registers approximately 1,360 watts per square meter. As the distance increases to 1.36 astronomical units, the point at which three-eyed Atlas would achieve its perihelion, this value diminishes to around 730 watts per square meter. Nevertheless, this remaining energy is substantial, more than sufficient to drive vigorous chemical reactions. For an entity that had endured billions of years in the profound chill of interstellar space, where temperatures hover mere degrees above absolute zero and sunlight is virtually imperceptible, this influx represented an immense shock. Even during its transit through our solar system, journeying inward from beyond Jupiter's orbit, three-eyed Atlas had never encountered such intensity. Furthermore, if the pronounced power law relationships governing its nickel and cyanide production proved consistent, and if these correlations extended forward, then the perihelion event was expected to trigger a spectacular eruption of gases, far surpassing any previously observed outgassing. The Solar and Heliospheric Observatory, or SOHO, has maintained continuous surveillance of the Sun since 1995. Strategically positioned at the L1 Lagrange point, approximately 1.5 million kilometers from Earth in the direction of the Sun, SOHO maintains an unblinking vigil over the solar disk and its immediate surroundings. Its LASCO coronagraphs are engineered to obscure the Sun's direct light, enabling the observation of the faint solar corona and the detection of celestial bodies traversing near the solar surface. SOHO has been instrumental in the discovery of thousands of comets, a majority of which are small, sun-grazing objects that plunge perilously close to the Sun's fiery embrace, often succumbing to disintegration. While the spacecraft was not explicitly designed for the study of interstellar objects, its orbital placement and sophisticated instruments rendered it capable of observing three-eyed Atlas as it navigated the inner solar system. The Parker Solar Probe presented an additional avenue for observation. This mission, launched by NASA in 2018, is meticulously designed to venture closer to the Sun than any previous spacecraft, aiming to unravel the mysteries of the solar corona and solar wind from within Mercury's orbital path. Its perihelion passes bring it as close as 6 million kilometers to the solar surface, a proximity so extreme that the spacecraft relies on a specialized heat shield to withstand temperatures exceeding 1,000 degrees Celsius. While Parker was not scheduled to be at its perihelion concurrently with Three-Eyed Atlas, the spacecraft operates on its own elliptical orbit, and their timing did not align. Parker's WHISPER instrument, the Wide Field Imager for Solar Probe, possesses a field of view expansive enough to capture objects within the inner solar system. Mission planners calculated that between late September and early November, WHISPER should be capable of observing Three-Eyed Atlas, at least peripherally, contingent on precise positional data and scheduled pointing. The inherent challenge with observations from both SOHO and Parker lies in their primary design. They are optimized for solar physics research, not for the detailed study of cometary phenomena. SOHO's coronagraphs, for instance, possess a relatively coarse spatial resolution. They can reliably detect the presence of a comet, estimate its brightness, and track its trajectory, but they lack the resolution necessary to differentiate a compact nucleus from an extended coma, let alone discern its shape or identify surface features. Parker's WHISPER, while offering superior resolution, was primarily engineered for imaging the solar wind, not solid celestial bodies. Furthermore, Parker's trajectory dictated that any observations of Three-Eyed Atlas would likely be from suboptimal angles, capturing the comet as a background element within solar observations rather than as a primary target of study. The spacecraft best equipped to provide definitive perihelion observations was ESA's JUICE, the Jupiter Icy Moons Explorer. Launched in April 2023, JUICE was on its trajectory towards Jupiter, a path that fortuitously placed it in an advantageous position to observe Three-Eyed Atlas in November, approximately 2 weeks subsequent to its perihelion passage. At this juncture, the comet would still be highly active, remaining sufficiently close to the Sun for outgassing to persist at elevated rates, yet distant enough to prevent JUICE's sensitive instruments from being overwhelmed by solar glare. JUICE carries an array of cameras and spectrometers specifically designed for the study of icy moons. These very instruments, however, are exceptionally well suited for observing comets. The Janus camera system is capable of capturing color imagery with a resolution sufficient to discern structural details. The MAGIS spectrometer can meticulously analyze the chemical composition of the coma across both visible and infrared wavelengths. The UVS ultraviolet spectrograph is adept at detecting gases that emit in the ultraviolet spectrum. The European Space Agency confirmed that JUICE would commence its observations of Three-Eyed Atlas on November 2nd, continuing through the latter part of November. They underscored that this campaign would yield the most comprehensive views of the comet in its most active state, when its tail would be fully developed and its brightness would reach its peak. However, JUICE's observations would commence after the perihelion event. Whatever transpired at the precise moment of closest solar approach, during those critical hours when solar heating reached its absolute maximum, would occur at a time when no spacecraft possessed an optimal vantage point. SOHO might capture fleeting glimpses. Parker might secure distant imagery, but the detailed, high-resolution observations essential for definitively answering questions about its structure, the dimensions and shape of its nucleus, and the symmetry or asymmetry of its outgassing, those crucial observations would be conspicuously absent for the perihelion moment itself. Ground-based astronomers were effectively rendered blind. Three-eyed Atlas was situated on the far side of the Sun from Earth's perspective, obscured by 147 million kilometers of incandescent plasma. No terrestrial or Earth-orbiting telescope could possibly observe it. The celestial geometry simply did not permit it. This significant observational void was not only a source of frustration for scientists eager to comprehend perihelion behavior, but also fostered a peculiar quandary for those harboring suspicions about Three-eyed Atlas's potential artificial nature. If a significant event, such as a planned maneuver or the activation of dormant systems, were to occur, the moment of maximum solar energy influx, while shielded from direct earthly observation, would represent an ideal window. Some had noted this possibility as early as July, when the object's trajectory was first calculated. Avi Loeb, in one of his published papers, drew attention to the fact that Three-eyed Atlas would be obscured by the Sun from Earth's vantage point during its perihelion passage. He posited that if an entity wished to conduct operations without drawing the attention of a specific planet, orchestrating perihelion to coincide with that planet's inability to observe would be a remarkably astute tactic. Naturally, this line of reasoning presumes a pre-designed trajectory, a premise that remains purely speculative. Natural orbital paths exhibit no regard for observational geometry from Earth. The circumstance of perihelion occurring when Earth is unable to witness the event is purely coincidental, a consequence of when Three-eyed Atlas entered the solar system and the specific trajectory it adopted. Imputing intent to this alignment necessitates belief in a meticulously planned journey, a conceptual leap unsubstantiated by empirical evidence. Nevertheless, the speculation persisted. Online forums buzzed with discussions. Could Three-eyed Atlas have employed a solar sail maneuver? The Orth effect, a genuine phenomenon in orbital mechanics, dictates that firing a propulsion system within a deep gravitational well, especially at high velocity, results in a greater change in kinetic energy compared to firing it in the vacuum of deep space. Consequently, performing orbital burns at perihelion is the most efficient strategy. If Three-eyed Atlas intended to alter its trajectory, transitioning from a hyperbolic escape path to a bound orbit that would retain it within the solar system, perihelion would represent the optimal location for such a maneuver. This would maximize the efficiency of its propulsion system, irrespective of its underlying form. Moreover, coordinating this maneuver to occur precisely when Earth's observation was impossible would afford plausible deniability. By the time the object re-emerged from behind the Sun and became visible to Earth in December, the maneuver would be complete. It would be following a new trajectory, but observers would require time to calculate its revised orbit and recognize the alteration. This scenario ventures into the realm of science fiction. Concrete evidence of deliberate maneuvering is conspicuously absent, yet the proposed scenario is physically plausible, a fact that rendered it compelling to a segment of the scientific community. The natural expectation for perihelion was equally dramatic. If Three-eyed Atlas was indeed a comet, and if the pronounced power law relationships governing nickel and cyanide production persisted, then perihelion was anticipated to precipitate a colossal outburst. Production rates had already escalated by a factor of 25 between late July and late August. Extrapolating this trend forward to perihelion suggested that production rates could increase by an additional factor of 10 or even more. Such a prodigious rate of gas release could profoundly alter the comet's visual appearance. The coma would expand significantly, potentially engulfing hundreds of thousands of kilometers. The tail, which had been faint and short in earlier observations, would lengthen dramatically as the solar wind and radiation pressure propelled dust and gas away from the nucleus. its brightness would surge, possibly rendering the comet visible to the naked eye, were it not for its concealment behind the sun. Thermal stress also posed a significant risk of fragmenting the nucleus. Numerous comets undergo disintegration at perihelion when the intensified heating causes internal pressure to build up at a rate exceeding the capacity for surface venting. If Three-Eyed Atlas possessed structural weaknesses, if its nucleus comprised a loosely bound aggregate of smaller components held together tenuously, the stresses encountered at perihelion could cause it to fracture. Fragmentation events are visually spectacular. The nucleus divides into two or more distinct pieces, each subsequently developing its own coma. The resultant brightening can be striking as fresh, icy surfaces are exposed to the sun's illumination. However, fragmentation also signifies the beginning of the end for a comet. The constituent pieces disperse over subsequent orbits, their collective surface area increasing, leading to a more rapid sublimation compared to their existence as a single entity. Fragmentation, in essence, represents a death sentence for comets, albeit a process that unfolds more slowly than immediate disintegration. Would Three-Eyed Atlas emerge from perihelion intact? The answer to this question would offer crucial insights into its structural integrity. A cohesive, solid nucleus, whether of rocky or icy composition, should theoretically survive. A rubble pile, however, might not. And if the object were artificial, possessing internal structural reinforcement beyond that afforded by random aggregation, this resilience would manifest in its survival. The period of waiting proved arduous. October 29th arrived. The day concluded. Three-Eyed Atlas traversed its perihelion, while Earth remained unaware, facing in the opposite direction, the sun itself obstructing the view. Spacecraft meticulously gathered what data they could from their distant or oblique perspectives. Somewhere within the inner solar system, concealed from our direct sight, something was occurring to an object that had journeyed for billions of years to reach this pivotal moment. Solar heating vaporized its ices. Pressure accumulated within the nucleus as gases expanded. Material streamed outward into space, propelled by sublimation, by thermal expansion, and by the unyielding force of solar radiation. Nickel atoms, if the established power laws held true, were being liberated at unprecedented rates, emitting a green luminescence as they fluoresced under ultraviolet bombardment. Cyanide radicals formed and subsequently dissociated through intricate chemical cascades. Dust particles were lifted from the surface, carried aloft by escaping gases, intercepting sunlight and reflecting it back into the void. And then, the perihelion passed. Three-Eyed Atlas commenced its outward journey. Its distance from the sun began to increase. The input of solar energy started to diminish. The intense activity characteristic of perihelion would gradually subside as the comet receded towards the frigid expanse of the outer solar system. However, the transmission of observational data back to Earth would require time. SOHO data would be downlinked and processed. Parker's observations would undergo analysis. The spacecraft were incapable of transmitting all collected information in real time. Data had to be stored, compressed, and then transmitted to Earth via the Deep Space Network's radio telescopes, subsequently received and decoded. Following this, scientists would need dedicated time to interpret the incoming information. Early November would yield the first preliminary perihelion observations. The JUICE spacecraft was scheduled to provide its crucial views during the second week of November. And finally, in early December, Three-Eyed Atlas would re-emerge from behind the sun from Earth's perspective. Ground-based telescopes would be able to resume their observations. The comet's post-perihelion appearance, its luminosity, its spectral characteristics, and its trajectory. All of these vital parameters would be meticulously measured, If its appearance after perihelion resembled that of a conventional comet, active yet adhering to predictable patterns, that would provide one form of answer. If it had fragmented, it would suggest inherent structural weaknesses, a natural composition incapable of withstanding the extreme thermal stresses. If it presented a markedly different appearance, if its chemical composition exhibited alterations, or if its trajectory displayed unforeseen deviations, these findings would undoubtedly prompt a cascade of new inquiries. The wait for December felt interminable. Weeks stretched into an eternity of uncertainty, characterized by reliance on incomplete data from spacecraft not ideally suited for this task, and by the observation of internet speculation spiraling out of control while concrete information remained frustratingly scarce. Scientists endeavored to temper expectations, reminding the public that data processing requires time, that preliminary findings can sometimes be misleading, and that scientific rigor necessitates patience. Yet, patience is a scarce commodity when the perceived stakes are so high. When an interstellar object might represent the most significant astronomical discovery of the century, or conversely, prove to be entirely unremarkable. When the definitive answer might redefine humanity's place in the cosmos, or simply add another data point to our ever-growing catalog of comets. October the 29th arrived and passed. The moment of perihelion faded into history, and three-eyed Atlas, whatever its true nature, continued its cosmic voyage, carrying its enigmatic secrets into the darkness beyond the sun, awaiting reobservation when Earth's orbital path would once again bring us into alignment. It waited to reveal whether it had survived intact, whether it had undergone transformation, whether the period of maximum solar input had indeed instigated any unexpected phenomena. It waited to provide, albeit partially, answers to the myriad questions that had accumulated through months of observation and spirited debate. Chapter 10. What transpires if our understanding proves flawed? Philosophers and scientists occasionally employ a thought experiment when contemplating existential risks. Envision being presented with a sealed container and informed that there is a 10% probability it harbors something that could precipitate the end of human civilization, while a 90% chance dictates it is entirely benign. Would you opt to open it? The majority response would likely be no. The stark asymmetry in potential outcomes renders caution the rational course of action. A 10% risk of catastrophe far outweighs a 90% probability of inconsequence. Now, consider a modification to this experiment. Suppose the container is programmed to open automatically in 1 month. You are powerless to halt this process. You possess the ability to examine it externally, conduct tests, and gather information that might aid in preparing for its contents. Would you investigate? Would you measure? Would you strive to comprehend, even if that comprehension might prove unsettling? This scenario bears a striking resemblance to humanity's current predicament with three-eyed Atlas. The object is present, traversing our solar system on an unalterable trajectory. It will eventually depart, continuing its journey through interstellar space. We can choose to observe it, or we can choose to ignore it. We can gather data, or we can embrace deliberate ignorance, but we cannot compel it to vanish. The Trojan horse analogy, invoked by Avi Loeb, resonates with historical significance. Around the year 1200 before the Common Era, according to legend, the Greeks laid siege to Troy for a decade without success. They subsequently constructed a colossal wooden horse, leaving it outside the city gates as a seemingly harmless offering, and then sailed away. The Trojans, convinced of their victory, brought the horse within their city walls. That night, Greek soldiers concealed within the horse emerged and opened the gates, facilitating the return of their army. Troy fell because its inhabitants readily accepted something they fundamentally did not understand. If three-eyed Atlas is artificial, if a discernible fraction of its observed properties genuinely points towards technological origins rather than geological processes, then its ultimate purpose remains unknown. The default assumption, the optimistic outlook, is rooted in scientific curiosity. An advanced civilization dispatches probes to explore, to gather data, to learn about other star systems, much as we have sent our Voyager and Pioneer probes beyond the confines of our own solar system. This envisions peaceful exploration, devoid of hostile intent. However, this assumption is precisely that, an assumption. We possess no means to verify intentions. An object that presents as a comet, yet is in reality a probe, could be engaged in intelligence gathering about our solar system, about Earth, about the very existence of life here. It might be transmitting data back, utilizing methods imperceptible to us, or operating on timescales too protracted for us to detect during its brief passage. Alternatively, its purpose could be far more concerning. The academic paper co-authored by Loeb with Adam Hibbert and Abraham Loeb, titled, "Is the Interstellar Object Three-Eyed Atlas Alien Technology?" explored scenarios where the object's trajectory and timing were not merely coincidental. It posited that the close approaches to Mars, Venus, and Jupiter served purposes extending beyond random chance, and that its perihelion passage behind the Sun allowed for maneuvers or activities concealed from Earth's observation. The paper was carefully framed as a pedagogical exercise, an exploration of possibilities rather than a declaration of probabilities, yet it outlined scenarios that were undeniably unsettling. If a civilization sought to conduct reconnaissance of our solar system, Three-Eyed Atlas's trajectory would be nearly optimal. Retrograde orbits are inherently more challenging to intercept. Close passes by multiple planets offer opportunities for gravitational assists to modify the trajectory or for the deployment of smaller probes that could potentially break into planetary atmospheres. The paper calculated that if Three-Eyed Atlas utilized a reverse solar sail maneuver at perihelion, it could potentially transition from an escape trajectory to a bound orbit, thereby remaining within the solar system indefinitely. The most advantageous timing for such a maneuver would be when Earth was unable to observe it, a condition precisely met by its perihelion passage. Is this what transpired? Currently, there is no evidence to support this hypothesis. Trajectory calculations necessitate highly precise positional measurements over extended periods. Until Three-Eyed Atlas emerges from solar conjunction in December and becomes observable once more, astronomers cannot definitively ascertain whether its path has been altered. Even if its path were to shift, the explanation could lie in forces unrelated to gravity, originating from uneven gas emissions. Comets regularly undergo minor alterations in their trajectories due to these outgassing jets, which generate a propulsive effect. Differentiating a naturally occurring change in an object's course from one that is artificially induced necessitates meticulous scrutiny of the location of these emissions, their uniformity, and whether the resulting forces correspond with observable vapor plumes. Such in-depth analysis demands considerable time and high-caliber observational data. Yet, this contemplation raises disquieting questions. Should an extraterrestrial probe aim to remain within our celestial neighborhood, perhaps to conduct investigations spanning decades or even centuries, what recourse would we possess to impede it? The stark reality is that we would be incapable. Our swiftest spacecraft traverse at mere dozens of kilometers per second. The object in question, which we've designated Oumuamua, is currently moving at speeds exceeding 60 kilometers per second relative to the Sun. We lack any means to intercept something traveling at such velocity. There is no propulsion system capable of matching its speed, nor any weaponry that could reach it. Even if definitive proof of an artificial origin were uncovered, even if we were absolutely certain that Oumuamua represented technology from an alien civilization, our options would be restricted to observation and apprehension. We could direct more sophisticated telescopes toward it. We might endeavor to establish radio contact, though the elapsed time for a signal to travel to an object several astronomical units away and return would render any meaningful dialogue impossible. We could inform international bodies, convene emergency sessions at the United Nations, and coordinate scientific efforts. However, in terms of concrete defensive measures, we possess none. If the probe's intentions were malevolent, if its purpose was to evaluate our capabilities prior to some future action, we would be utterly helpless to prevent subsequent events. This is precisely why some advocate against overly assertive observation. If we are indeed under scrutiny, if our radio and television broadcasts have already broadcast our presence, does focusing telescopes on an interstellar visitor alter anything? Or does it merely signal that we have taken notice, that we are paying attention, potentially provoking responses we cannot foresee? Conversely, others hold a different view. Ignorance does not equate to security. If an object of potential technological origin is traversing our solar system, acquiring as much information as possible is paramount. Understanding its capabilities, its composition, its behavior is crucial. Such knowledge could prove vital should more such entities appear in the future. We cannot defend against what we fail to comprehend, but we might be able to prepare if we acquire sufficient understanding. The philosophical ramifications extend far beyond immediate security concerns. Confirmation of Oumuamua's artificial nature would signify that we are not alone. This would not be the abstract belief that life likely exists elsewhere in the cosmos, but the concrete knowledge that another technologically advanced civilization exists and possesses the capacity to dispatch objects across interstellar distances. Such a revelation would fundamentally reshape humanity's self-perception. We would no longer be unique. Our accomplishments in science, technology, art, and philosophy would necessitate recontextualization against the backdrop of others who have likely achieved far more, given their mastery of interstellar travel, while we have barely ventured beyond our own moon. Some might find this humbling in a positive sense, a reminder of our diminutive place within a vast universe, serving as an impetus for our species to mature, to transcend our divisions and conflicts. Others might perceive it as a threat. If we are not solitary beings, if we are potentially being observed or assessed, then our future may not rest entirely within our own dominion. The societal consequences would reverberate through established institutions. Religious doctrines would need to reconcile their tenets with the existence of extraterrestrial intelligence. Governments would face scrutiny regarding their preparedness and their failure to seriously consider such a possibility. Scientists would redirect their focus toward understanding the implications, toward discerning the feasibility of communication or the wisdom of maintaining silence. Economic impacts, while perhaps subtle, could be substantial. The existence of technology vastly superior to our own would alter long-term investment strategies. Should we continue developing certain technologies, knowing they might become obsolete if we ever gain access to alien knowledge? Or should we accelerate research, striving to advance as rapidly as possible to narrow the technological disparity? Military doctrines would require a complete overhaul. If potential adversaries exist with capabilities we can scarcely fathom, then Earth's geopolitical disputes become largely irrelevant. The concerns over territorial disputes with neighboring nations fade into insignificance when confronted with the possibility of interstellar powers monitoring our planet. However, all of this hinges on the assumption that Oumuamua is artificial, and the prevailing probability, as most scientists would contend, remains low. The observed anomalies are indeed present, and the observations are perplexing, but natural explanations, however tenuous, are still considered more probable than artificial ones, primarily because we lack any prior evidence suggesting the existence of interstellar probes. The potential cost of error, however, is asymmetrical. If we dismiss it as natural and are mistaken, we forfeit an opportunity to learn, to communicate, and to prepare. We might remain oblivious to a presence within our solar system until it acts in ways we can no longer ignore. Conversely, if we treat it as potentially artificial and are incorrect, we will have expended additional observational resources, published some erroneous research papers, and potentially appeared foolish to future historians. The consequence of assuming a natural origin when it is artificial carries a far greater potential cost than treating it as artificial when it is natural. This inherent asymmetry justifies heightened caution, increased observation, and more thorough analysis. It justifies taking the possibility seriously, even if the estimated probability appears low. In early December, as Oumuamua becomes visible from Earth once more, enabling telescopes to resume their observations and calculate its trajectory following perihelion passage, we will acquire new data. If it has fragmented, this would strongly indicate a natural origin. Artificial probes do not typically disintegrate due to thermal stress. If its trajectory exhibits no unexpected deviations, this increases the likelihood that it is a comet behaving according to purely gravitational influences and outgassing. Should its chemical composition remain unusual, if the nickel emissions persist, and if its color and structure continue to generate more questions than answers, then the debate will undoubtedly continue. And if, in the scenario that preoccupies some scientists, its trajectory reveals changes inconsistent with natural outgassing, if the object has executed maneuvers implying deliberate thrust, then the entire context will shift. The Galileo project, under the direction of Avi Loeb, was established to investigate potential evidence of extraterrestrial technology, encompassing both historical artifacts through the study of interstellar objects and current phenomena by monitoring for unidentified aerial activity. The project operates 3 observatory facilities equipped with instruments designed to detect and characterize anomalous objects. Should Oumuamua exhibit any unexpected behavior upon re-emerging from solar conjunction, the Galileo project's telescopes will be observing. This will be mirrored by dozens of professional observatories worldwide, as well as thousands of amateur astronomers with their backyard equipment and unwavering dedication to comprehending the cosmos. The observational campaign surrounding Oumuamua's reappearance will represent one of the most concerted efforts in the history of astronomy. Its impetus stems not solely from scientific curiosity, but from the persistent suspicion that this object might be more significant than it initially appears. Between now and December, the period of waiting persists. Data from its closest approach to the Sun are slowly being disseminated. Scientists are meticulously analyzing SOHO observations frame by frame, searching for any irregularities in the comet's appearance or behavior during its perihelion passage. The JUICE spacecraft is preparing its instruments for November observations, with mission planners calculating optimal pointing angles to maximize data quality. Meanwhile, individuals speculate in online forums and casual conversations within university lecture halls and government briefings. The fundamental question remains: what is Oumuamua? Is it a celestial rock or a manufactured probe, an ancient comet or ancient technology, a random wanderer or a purposeful explorer? The eventual answer may not be absolute. Science rarely provides definitive certainty, particularly concerning objects observed remotely with limited data. However, the pursuit of that answer, the process of accumulating evidence and evaluating possibilities, continues unabated because understanding what passes through our solar system, understanding whether we are alone or observed, understanding the nature of interstellar visitors, these questions touch upon the most profound aspects of human curiosity and our position in the universe. As December draws nearer, the comet continues its celestial journey, and we await its emergence from behind the sun. And so, we find ourselves at this singular juncture in human history, gazing at the heavens with instruments our ancestors could only have dreamed of, seeking answers to questions that transcend mere science and touch upon something far deeper. Oumuamua proceeds on its path, unaffected by our debates, our apprehensions, or our aspirations. It travels through the darkness beyond the sun, carrying its undisclosed truth, awaiting reobservation when orbital mechanics once again align our perspectives. We have collectively examined the evidence, the elongated images from Mars that initiated an ongoing debate, the coordinated reticence from global space agencies, rivals united in their reluctance to share information, the unexpected green luminescence devoid of the necessary molecular compounds, the ejection of nickel into space at rates defying conventional explanation, the accumulation of 7 statistical improbabilities akin to evidence in an unresolved trial, the hushed discussions at political echelons where decisions regarding disclosure are made, and the efforts of amateur astronomers who have stepped into the void with images of varying clarity and interpretation. Furthermore, we consider the perihelion passage, obscured from our direct view, where solar energy bombarded a surface that had endured the frigid emptiness of interstellar space for eons. 2 primary interpretations remain, either an elongated physical object or a photographic artifact, an ancient comet possessing heretofore unknown chemical properties, or something that merely imitates a comet while being fundamentally distinct, natural or engineered, serendipitous or deliberate. Perhaps December will illuminate the situation. Perhaps post-perihelion observations will reveal fragmentation, chemical alterations, or trajectory deviations that finally tip the scales toward one conclusion. Alternatively, the ambiguity may persist, and Oumuamua will join that growing roster of cosmic enigmas where evidence points in multiple directions and definitive certainty remains elusive. What we can state with certainty is this: an entity from beyond our solar system has traversed our cosmic vicinity, an object of immense age, composed of materials formed around a distant star and shaped by processes billions of years removed from our experience. Whether it serves as a messenger or represents a mere coincidence, whether it conveys information or simply reflects starlight, it serves as a potent reminder that the universe is vaster and more extraordinary than our everyday existence allows us to fully grasp. Thank you for dedicating these hours with me to exploring the evidence and the profound implications of this remarkable visitor. If you found this journey insightful, I would be grateful if you would consider liking this video and subscribing to the channel. It aids in bringing these narratives to a wider audience and supports the creation of more in-depth explorations into the mysteries that surround us. The content presented here is derived from publicly accessible data, published research, and documented observations as of October 2025. Scientific understanding is a dynamic process, evolving as new evidence emerges, and interpretations deemed plausible today may be revised or disproven by future discoveries. This video examines various possibilities and presents multiple viewpoints, but it does not present definitive conclusions on matters still under investigation. It is always advisable to consult multiple sources, maintain a skeptical outlook, and acknowledge that for many questions concerning Oumuamua, the most accurate response remains, "We do not know." The night sky continues its ancient celestial ballet above us. Stars trace their predetermined paths. Planets wander across the backdrop of constellations. And somewhere in the vastness, beyond the sun's blinding glare, an interstellar visitor continues its transit through our cosmic neighborhood, holding its secrets close, awaiting the moment when orbital geometry realigns us for further observation. Rest well and continue to observe the skies. Good night.